Okay, we are live, hopefully. Hello everyone. As usual, if audio doesn't work or something like this, please say so in chat. Hopefully things are working fine. If somebody can just say that audio does work in chat, that would be good as well. We were on a break for a few weeks. I was traveling, it was fun, but we are back to other things that are fun. And today we are gonna look, sort of continue from where we left off last stream and look at ray tracing, look at ray tracing performance, talk about why we are seeing somewhat disappointing results, try to fix some of the things that are wrong, and also hopefully take a little bit more time to dive into the details of the hardware implementation. So last time on stream, I kind of did a bit of ad hoc, like let's look at some profiling results and try to understand what the driver does. Over the break, I looked more into that for AMD hardware specifically, and so we're going to look a little bit more into that as well. So to remind people where we left off last time. So we have code that we can still run as before. So we load like a GLTF scene, we render a scene. It's some very basic shading, there is like nothing super interesting here. We did do bindless support like a stream before the last stream, and so because of this we have textures and normal maps and stuff like this. And last stream we were working on this thing where we take the geometry that we have in the scene, build various acceleration structures from it using Vulkan APIs, and then use a Vulkan extension to ray trace a single ray per pixel in the fragment shader. And the issue that we ran into, or sort of the problem, the most obvious problem to solve, is that the result works, it renders fine, but it has poor performance. So right now I'm using the RADV driver. There's two drivers on Linux hardware for AMD: RADV, which is an unofficial driver, part of Mesa, and AMDVLK, which is an official driver from AMD that's very, very closely matching the Windows driver. And I actually tested this, that on Windows, I'm getting like basically the same performance in the Windows driver, official driver, versus the AMDVLK. This is good because AMDVLK has source code. I didn't get into, in theory, you can build it and do the same things that we were doing with RADV, like you patch the driver and see what happens. I didn't do the build setup, and it's more complicated than Mesa's. So we're not going to do that today, but we might look at some source code. So we have the scene renders. It renders at 12 milliseconds for this window, whatever the window size is. I'm not actually sure. But if we do a full screen window, then it renders at like 23 milliseconds. So that's like slow. Without ray tracing, the full screen renders at like 1 millisecond. So that's a big issue. One reason why this is a big issue, not only do we not make 60 FPS in like 4K, my screen is 4K resolution, by the way, like the YouTube stream is not 4K, but the screen that I'm rendering at is 4K. So not only do we not get 60 FPS at 4K, we are doing 1 ray per pixel with just shadows, and it would be nice to do more, right? As in, I think the bare minimum, or not the bare minimum, the idea behind the things that we are doing is to do as much sort of complex effects as we can with ray tracing. For example, I don't want to do shadow maps, so I want to have ray tracing for sun shadows. I want to have in the future ray tracing for point light shadows and stuff like this, reflections. So ideally, you'd have more than one. Now, you want a small constant number of rays per pixel. Like maybe you want an average of like 4 rays per pixel or something like this. But like even with just 1 ray, things are not fast enough. Now, this is not the top end GPU on the AMD side. This is 7900 GRE, which is I think around 7800 XTX. It's like a cut down card from even XT version. So it's, you know, not like the top GPU. And it's not an NVIDIA GPU. NVIDIA, sort of the situation with performance on NVIDIA's hardware would have, especially 4090, would have been better, but this is not quite practical, right? So now there is a question of sort of why. One thing that we did do last stream is we installed the official AMD driver and tried with that. So let me do that as well. And now I have the official driver just set up as the default driver. So whenever I want to do RADV, I have to like specify that I want a custom driver build. So with that, the 4K version is almost twice as fast. It was like 23 milliseconds there and like 13 here. This points at a significant difference between the RADV driver and the AMDVLK driver in terms of ray tracing performance. We are going to talk about some of this in the late half of the stream. And because of this, we are going to switch to the official driver for a bit. But even 13 milliseconds with 1 ray per pixel at 4K is like not good enough for what I want to do, right? Because again, you do 4 rays per pixel, like at best you're looking at, what is it, like 60 milliseconds per frame. This is not a good target. I thought that things like this would happen, and we even did a little bit of, like, I didn't talk about this last stream, but I hinted at, you know, like some stuff that we might have to do. So let's look at one of the problems. Let's assume for a moment that the AMDVLK implementation is perfect, as in the 13 milliseconds is as good as it gets with our current approach on this hardware. I don't know if that is true. For example, if you disable ray tracing, RADV is like 5% faster or so than the official AMD driver, so it could be that the official driver could be even better. But that's the only thing we have. This is the best thing we have. 13 milliseconds is too much. So one thing that I did do last time, but I didn't explain anything. Let me do a render doc capture. I really should fix this at some point. To do a render doc capture, I have to like rebuild without Wayland, because things are, because like render doc doesn't support Wayland anyway. And now it doesn't work. Huh? Oh no. That is weird. Hold on. Oh, is it because I switched the driver? Interesting. Oh, wait. We have to disable ray tracing. Right, sorry. Render doc doesn't support ray tracing, so we have to, okay. One other issue that we'll correct on this stream as a byproduct of some stuff is we currently have to hard code like is ray tracing enabled or not in the shader, because I didn't want to deal with the shader situation. So here's our scene. For now, I'm just going to use the smaller resolution to not have to maximize all the time. So this is with ray tracing off, so it renders very quickly. With ray tracing on, the additional workload is the fragment shader gets way more expensive. So one thing that we did do last time is look at, perhaps here. No, wait, look at, so there's a small issue in visualizing some of the stuff where we have 3 render passes, and because of this we can't sort of have the full scene visualization, but that's fine. So render doc has this view, and this view is called quad overdraw, and it kind of combines 2 types of overdraw that you would expect to have in a rasterized renderer. Let me look at the, yeah, so this is 4 and this is 1, cool. So what are these? It's interesting that it's 4. This is 1. Kind of of expected this to, oh no, this is 3, okay. Interesting. Anyway, so what are we seeing right now? So RenderDoc does this, has this mode where it does a special visualization. There is a separate buffer that it renders to, and in this mode, and it uses like a read-write buffer to do an atomic increment on every pixel that's been shaded. And as a byproduct of this in every pixel, you get the number of times that the fragment shader has been ran for that pixel, more or less. You can see that for a large part of our scene, like this bottom half, things are decent. Well, for pixels like this, you have basically one. I'm not sure that you can see, maybe the stream window hides it, but like in the bottom right, when I hover over a pixel and press like the right mouse button, it updates like the color, and the color is the number of hits that the fragment shader ran for, number of times fragment shader ran for. So for a lot of these, the value is 1 in the bottom half, which is good. The fragment shader runs 1 time, you know, it's like the smallest number of times the fragment shader can run for a pixel that is actually covered by anything. For a large part of our scene, we see worse results. So in the building here, actually, we see some values that are like between 3 and 5. I'm actually confused a little bit as to why it's 3. I don't know if the geometry is super optimal here. There's maybe some stuff that is not ideal in the way that the scene is constructed, I'm not sure. But clearly, the results are not perfect for some of these. But then there is these areas like these where the values are high. So for example, this pixel is being shaded like 26 times. There's a few reasons for why this might happen in a scene, and some of them are more avoidable than others, and some of them are less avoidable. So there's kind of 2 problems here. One is that in some of these, like if you look at this, this is a large flat triangle, but clearly there's some geometry behind it that's still being rendered. We have occlusion culling implemented, so in theory, geometry that's behind other geometry shouldn't be rendered ever, and so we shouldn't have this problem. But in practice, the geometry or the occlusion culling is not per triangle, and it's based on this simplified version of the depth buffer, which means that especially large triangles that are hidden behind other geometry that are really close, that are like not visible, but really close to the occluding sort of, to the part of the mesh that occludes it, would still render. So that's kind of what's going on here. Now, in some cases, I would expect maybe better results, like in these areas, maybe I would expect better results. So maybe at some point we should like debug what's happening here and stuff like this. But there's clearly worse issues than these bits. If you look here, right, there's like a ton of complexity here in the shader invocation count. And one of the reasons why this can happen is the quad overdraw. This is why the mode is called quad overdraw, in addition to the regular overdraw. When the GPU renders a triangle, it shades pixels in groups of 4. And even if the triangle is small and it only covers 1 pixel, the GPU will still shade 4 pixels. And there's reasons for why this has to happen that have to do with the gradient computation. We will not cover like that. You can find plenty of information online, but this is the part that is hard to avoid. So when we talk about the general overdraw, what we could do is we could have a Z prepass. It would essentially entail us rendering the entire geometry of the scene again. Sort of in the first pass of the geometry, we would just write to the depth buffer, and then in the second pass, we would actually run all of our computations. This is possible to do, and it should fix the overdraw situation sort of comprehensively. But it won't fix the quad overdraw problem. The quad overdraw problem, if you look at these, for example, pass, the quad overdraw problem gets especially unfortunate if, and this particular thing is maybe we can fix, but There is another issue besides sort of quad overdraw, which is when we render triangles with an alpha test, even pixels that will be rejected by the alpha test currently go through the shading process. And one, they actually cast rays, I think. I don't remember what the fragment shader is doing. Yeah, the fragment shader, like at the very end, discards the pixel if the alpha is less than 0.5. We could move this to happen earlier in the shader, but the problem is the way the hardware works is it groups these quads that are 4 pixels into larger units called like warps or wavefronts or something. And in general, you want similar amount of computation happening for every pixel in this warp. So even if we were to early out from the shader when the alpha is like less than 0.5, it would still result in poor efficiency because you'd have this warp where there's like 32 pixels and out of them maybe 16 are not doing anything because they're like in the regions with alpha set to 0, but with the texture alpha set to 0, but the GPU is processing the entire warp, and so the warp is still not running very efficiently, even though you think you're saving time, you don't, or you're saving less time. So all of these problems are, some of these problems get better when you enable depth prepass, but some of them don't. One other issue in the scene, and you can see this here, right? So what is this geometry? This is a decal. I think I talked about this last time, or maybe two streams ago. Some of this scene has decals. Decals are just geometry here that is layered on top of other geometry. And right now we are using alpha test on it. We should probably do a blend. But whenever you have decals, if you shade if you do shading in a fragment shader, you will shade a pixel multiple times just because there's going to be multiple sort of layers for every pixel that you have to go through. And if you do ray trace for every one of them, that becomes more expensive. So all of these are not really because we are doing ray tracing per se, but just because of how we are doing the shading for the scene. And depth prepass could solve some of them at the cost of having an extra geometry pass, but it wouldn't solve quad overdraw. And traditionally, the way people talk about solving quad overdraw is, oh, you can have simpler geometry. The problem for us is, A, we have somewhat dense geometry to begin with in some parts of the scene. B, although we do level of detail, we do level of detail assuming that if we want it to look exactly the same as sort of it looks like without, like the scene, enabling level of detail shouldn't change the appearance of the scene, which means that for an object that's even somewhat far away, you still want triangles that perfectly represent the silhouette of the object, which means that they're going to be really, really small. So there's a few examples, and again, like doing depth prepass would help with some of this, but it wouldn't solve some of these issues for good. Because of the extreme deficit of performance with ray tracing that we have, I kind of want a solution that does the absolute minimum amount of work possible regardless of the geometry in the scene. There is a couple solutions that people use in the industry for to fix this problem, and there is a spectrum of those, starting from deferred shading and then going into like visibility buffers and stuff like this. Notably nanite, which is like a kind of hierarchical cluster level of detail technology in Unreal, has to grapple with a similar problem. In part, it's because they have a software rasterizer, but the reason why they have a software rasterizer is that they want triangles that are really small because they want dense geometry to be represented perfectly on screen. And so because of this, they run into all sorts of these bottlenecks that we are now running into as well. And the solution that they come up with is they use a visibility buffer, and which we could do, but visibility buffers tend to be a little bit more complicated to implement. So I think what we should start with is we are going to convert our pipeline to be a deferred shading pipeline. Somebody actually asked about this, I think last stream, and I said, yeah, I don't know, but like if we have to do deferred shading, we will do it. So I guess we'll do it now. Deferred shading should solve all of these efficiency issues, because the way deferred shading will work is that we'll first render all of our geometry without doing any ray tracing, just filling a bunch of buffers with data for every pixel that's kind of comprehensively covers what should happen there during shading, and then we'll have a separate pass that shades every pixel. Deferred shading will have issues in the future in the sense that it will make transparent geometry, like it's unclear how to do transparent geometry in the deferred shaded setup. Even right now we have issues with transparent geometry, which is why we don't implement it, because transparent geometry has to be sorted and it has to be drawn separately, and because our entire pipeline is GPU driven, it's like more difficult to sort. But like we could do it if we wanted to, and doing deferred shading means we have to change a bunch of stuff. The good news is transparent sorting is kind of broken in computer graphics anyway. If you have like two overlapping triangles, or if you have two objects that are too close to each other, sorting will not work correctly. And so whenever we get to translucency, it might make sense for us anyway to explore something that is not the traditional sorted geometry rendering anyway, because the traditional sorted geometry rendering has problems. So for now, we will not worry about this. We don't have transparency. We will not have transparency. The only thing we have is alpha test, and that will work just fine. So that's kind of the plan for today. Rework things to do a deferred shading setup. Hopefully performance will get much better, and then we will look a little bit closer at the differences between the two drivers and why they might happen, and maybe think about what we can improve ourselves in the future as well. So that's kind of the preamble. This stream has nothing to do with Roblox as usual. I haven't worked with Roblox for a year now, people. So one thing I wanted to do. Oh yeah, right. So so that's kind of where we are. So last stream we basically did like basics, ray tracing basics, and then we really need to fix ray tracing performance, and then there's going to be a bunch of other stuff for ray tracing that is sort of related to these two bits. Oh, right. One other issue I wanna note is this. So the reason why I thought we might have to do something deferred anyhow has to do with denoising. So what we do right now is we just render a ray per pixel, and then we use the fact that it hit the geometry or not to do shading to like see if the object is in shadow. And because of this, we have these really hard pixel perfect shadows. Pixel perfect shadows, like hard pixel perfect shadows, are cool, but oh, I have to go to Wayland again because like performance numbers are all different. But how interesting is this? Yeah, this is different. Cool. For like aesthetical purposes and also for visual correctness purposes, depending on how you look at this, you might want to do soft shadows. Soft shadows in this setup would either require us to do way more than one ray per pixel, or we do like one ray per pixel with some jitter and then have the entire output and then denoise it somehow. But it might be better in some cases to just be able to denoise only the shadows, or once we go into ray tracing, into reflections, maybe only denoise the reflection output and then blend the denoised output back into the scene, compose it back. Things like this are difficult to do when you shade things in a fragment shader, because you're kind of fundamentally thinking about, oh, what should the final color of a pixel be? Whereas with denoise, it's more like here's a bunch of inputs into the denoiser and here's the denoised output, and then it feeds back into the shading process. I don't think there's a strong conclusion in the industry on how to do these things right now. I've seen both the renderers that do denoise on individual components, so like denoise rate reflections, denoise shadows, and then compose everything back in, and renderers that say, oh no, we'll have a pixel that's like the final output of the pixel, which is going to be noisy, and then denoise the whole output. I don't want to lock into either solution, but the deferred solution will allow sort of any hybrid. And the benefit of having only partial denoise could be that whatever visual artifacts are from the noise that you see are kind of limited to just that component. So we'll see how this works. We're not going to do denoising for a while, I think, so just because there's so much other stuff to do. So that's like not crucial yet, but I just wanted to mention this. The final thing I want to mention for people who are tracking this project is I'm switching to the mode where I do a little bit of work off stream for things that are sort of interesting to explore for me, but maybe not as interesting to cover on stream. There's a couple things that I changed that just people might be aware of. First, in the bindless stream 2 streams ago, we were doing combined image samplers, and I switched to separate image samplers in a commit at some point. The diff is very, very simple, but all this means is that whereas before we had this array of sampled images in the shader, now we have an array of texture objects and a single sampler. Performance-wise, it's identical in our setup. It makes some things a little bit easier to do and some things a little bit harder. There's a few reasons why I did this, which I won't go into, but it's just like, be aware that this thing has changed a little bit. And then I went over this like SpearV parsing hack where I just had to debug a little bit because I forgot how SpearV works. And it turned out it's just like one extra line. This one extra line was missing when we were doing the stream. So that's fine now. And finally, one thing that I did last stream was when we were building the acceleration structures for the bottom level for the triangles. There's these 2 buffers. There is the buffer where the geometry lives, or the, not geometry, but like the actual final tree lives. And there's a scratch buffer that you only need temporarily. And the scratch buffer was like big. I think on one of the drivers it was bigger than the actual BH buffer. So I reworked things a little bit so that the scratch buffer is used more optimally. Basically, the way this used to work is that you have like a mesh 1, 2, 3, 4, 5, 6 that are laid out in the final acceleration buffer. So this is where the blast goes. And then we had a scratch buffer that had a unique slice of bytes for every mesh. So like this, right? Something like this. And we just allocated the scratch buffer for like all of the objects. So now I allocate the scratch buffer to share the scratch space between some of the objects, and the blasts are built in batches. So the way this works now is, I'm not sure how to draw this so that it's not confusing, but like let's say right now we can build 3 objects in a scratch buffer of 32 megabytes. And we do that, and then we have a barrier that says, let's wait until we built all of these 3. And then we build like 4 more, let's say, that also fit into 32 megabytes of scratch. And then we do another barrier, etc., etc. This, confusingly, is actually faster for AMD. I think it's because the cache utilization of the scratch buffer is much better now, because you don't have to fill like 400 megabytes of scratch data. You only have to reuse the 32 megabytes. So I mentioned this just because the code that we're writing on stream has changed a bit, and this is a problem I talked about last stream, but didn't solve. But I won't go over the actual code. It's like very straightforward. So that is kind of it for the introduction. So now let's go over the over what we are going to do. So right now we have these 3 passes that render geometry, and they fill a color buffer and a depth buffer. And then we have a final pass somewhere here, this probably, that takes the color and just copies it to the swap chain. And the reason why we did this way back when is just to make working with swap chains like a little bit less annoying, because this meant, why did we do this? I think this was before we started using dynamic rendering, and so managing multiple like render pass objects was painful, so I just like render into the same image and just copy. This is going to be good now for us, because right now we have this compute shader that we maybe will look at. Wait, how do you do this again? All right, that's fine. I don't love this disassembler. Let's just look at the actual shader. So we have this compute shader. It's very, very simple. All it does is it samples the color image that we have rendered to, and then writes the color to the swap chain, which is the exact same color. So, which means that we are kind of already set up to do deferred shading, because we could change this compute shader to do something much more complicated. Now, to do something that's much more complicated, we need more data. Because if you look at the fragment shader, at what it does right now, even though it's fairly simple, when we do ray tracing, we have the ray tracing result, which to compute that, we only need the position in world space of the pixel, and that you can recover from the depth information. So that part is fine. But then we take the result, we like fudge it somehow, but then we multiply that by the n.L factor, which depends on the normal. Then we multiply that by albedo color, and then we add emissive. And that formula is already not decomposable, in the sense that if we just remove the ray tracing and then we separately compute the shadows, and then we just multiply the color by the shadow color, no, by the shadow like attenuation factor or whatever, and this already will not work, because we want to add emissive color after the shadows. And if you are confused by the emissive portion, because it may not be like obvious in the scene, let me just remove this. Then I will note that these sign, the letters, the le petit coin, or whatever this says, these are actually using emissive, and if you remove the emissive, these would be darker, like these letters would be darker than these, because they're like in shadow of something, I guess of this balcony, and they would be like less visible. We can remove the emissive. Where is this again? And sort of show. And this is a trivial visual difference, relatively speaking, but obviously, yeah, so see, the not only are the letters much darker, now these letters are brighter than these because they're in shadow. So like the emissive factor fixes this, and we can't like compute that in the fragment shader and then do ray tracing after. And obviously our shading is very, very simple right now. What we actually want is more lights, we want reflections, and like for all of this to work, the shader has to know all of the data in the pixel. But the data that it needs to know is the data that we could save into the color buffer. For example, we have the normal, and we could just save, where is this? The normal into the color buffer, and then our compute shader will have access to the normal, right, to these values. But what we want in the shader is to have access to the color, the normal, the emissive color, and like some other stuff. And the way to do this is to switch to rendering to multiple color buffers at once using the technique called multiple render targets, I guess. And then in the compute shader, we'll have multiple textures. Each texture will have one texture will have the albedo, one texture will have normals, etc. And then the computer shader will be able to do the full thing. The other reason why this is nice for us is I really didn't want to do this ray trace enabling Boolean as like a specialization constant, just because it gets annoying. We don't have a full shader variant set up in our renderer yet, and you have to duplicate a bunch of code to be able to do this. But moving the ray tracing out of this shader kind of decouples things better. Now we'll have the code that just renders the G buffer, which is the perfect complete representation of the image like attributes. And then we have a separate shader. We will have a separate shader that does the shading, which will do the all of the ray tracing and stuff. So that is the plan. Deferred shading in general is not a modern technique. It's been used in games for many years. I think the first, is it 2006? No, 2006 is PS3. I thought they might have been in an earlier. It's probably a 20-year-old technique, basically. So I won't go too much into like the details, but I will mention that I just want to write the code, but I will mention that there is kind of one caveat besides the transparent objects that deferred shading has, and this is the kind of what data do you store in each pixel question. There's no right or wrong answer to this. It kind of depends on the renderer and what you want. And you would, ideally you want to minimize the amount of bytes that you store for every pixel so that you reduce the cost of deferred shading. The cost of deferred shading is that right now all of these values are in registers on the GPU when the fragment shader runs. And we then use these registers immediately to compute the final output color. But so the memory bandwidth cost right now is kind of zero in that sense. But with deferred shading, we have to first save all of this data, well, some of this data, to memory, to textures, and then load that back in. And so that's more bandwidth intensive. Because of the extreme cost of ray tracing, it should more than pay for, like, whatever extra time we take to render all of these buffers should more than pay for the improvements in efficiency. But that's kind of a thing to be aware of. And because of this, I think for now I'll just do like a very basic G-buffer setup, but we might need to refine this as we go in the future, because there's this fundamental trade-off. You end up thinking, okay, I need this extra bit of data in the shading path, but I don't want to spend too many bits on it. So where do I pack it? Where do I store it? Does it have to blend well, etc.? Like, there's trade-offs associated with this. So for now, we'll just do something very basic that works in our setup. I think what I'm thinking of is right now is I'll just do two. So we need albedo, which is three basically 8-bit values. We need the normal, which depending on how you work with this, at the minimum it's 3 8-bit, not at the minimum, the most basic encoding is like 3 8-bit values. This is actually not, this should be good enough for what we do right now, which is just diffuse, but this should not be high enough precision for specular in many cases. So ideally you want more precision. And you don't need 3 values, you can just do with 2 with octahedral encoding. So the scheme that I've seen people use successfully is use 2 10-bit channels. And there's this format called RGBA 10, 10, 10, 2, where you have 4 channels, 3 10-bit and 1 2-bit. You can store normals in these, and then you can store something else in these 2 others. I'm not sure what yet. And then we also need, so in our current shading scheme, there's also emissive, which is a color, which is 3 8-bit values. And then there's also specular, which is color plus loss. This is just how the scene is constructed. I don't love this. Ideally, we would use metallic roughness. The scene doesn't have these values, but we might be able to fudge some of them, because like you can sort of lossily convert between these. Some materials don't look quite the same. Anyway, like, it's complicated. But so but what I'm saying is essentially right now, the very naive version of the G buffer would just look like, let's have 4 textures, albedo normal, emissive specular, and we'll just store the data there as is. But I don't want to do 4. In fact, I might want to just do 3 right now, because what I'm thinking is emissive, in theory, is a color that's completely uncorrelated to albedo. I think in practice, there's kind of 2 useful emissive modes. One is you just use the albedo color, like scaled by some constant, and the other one is you do maybe white. So I'm thinking maybe I'll just do a single scalar for this for now and assume white emissive, and then we'll fix things in the future somehow. And then so that might mean that we can do albedo plus emissive 1 8-bit value. And then if we pack normal like this in the first 2 channels, and I think we can use this to store specular. The most important value is roughness, which we don't have, but it's kind of related to gloss. And then metallic in theory is just 1 bit. And our specular model is different. Anyway, so I think for now, I kind of just want to see what happens is if we just have 2 textures instead of 1. One packs albedo emissive and one packs normal, specular, like roughness, etc. I think it's very, very likely that we will end up adding a 3rd texture in the future. But I kind of want to do this knowing that we need to, and knowing what the cost would be and what the benefit would be, instead of just immediately going for 4 textures, we'll figure it out later. Just because, as I mentioned last time, I think somebody asked some question around this. The spirit of this entire series is like minimalism to the extent that you can get there with maximal performance and maximal sort of quality for the performance that you're spending. Ray tracing kind of deviates from this, because ray tracing eats so much performance, and then you could have other ways to achieve similar quality for similar effects. For shadows, we could do shadow maps, but we're not doing this. But ray tracing aside, I think I'd like to try to do things as minimal as we can, especially because if you do deferred shading, like there's a possibility that you don't do ray tracing at the end, you just do shadow maps at the end with the same G buffer. So anyway, so that's the plan for today. Let's just do 2 textures instead of 1. Let's pack things this way, and then let's kind of see what happens. All right, so I think we are ready to write code. Yeah, so can visibility buffer approach be combined with deferred shading? You can, and in fact, Nanite does this. I forget. So somebody mentioned John Cable's presentation. I forget if it does deferred or not, but it does do visibility buffer, which is great. But Nanite actually does visibility buffer plus deferred, because the way Nanite works is they have the Nanite renderer, which has like a software rasterizer. Oh, my handwriting is fantastic today. Which has like a software rasterizer. Because it's a software rasterizer, it's hard to do a G buffer like raster because of because of the atomics that they have to use. So instead, they do a visibility buffer which relies on a 64-bit atomic, which is like a 32-bit triangle ID basically, and 32-bit depth. Plus or minus, don't quote me on this, it's not quite exact. And then the rest of the Unreal Engine 5 pipeline is deferred. And in fact, you can combine Nanite with non-Nanite meshes in the same scene. So then they have a pass that goes from this to the G buffer. And then they can render more geometry to the G buffer from non-Nanite stuff. And this is kind of the beauty of the G buffer over visibility buffers, etc. The G buffer is a complete representation of the scene as it's seen from the camera perspective, with the exception of transparent geometry, but visibility buffer doesn't handle transparency either, it's just a single layer. Having a complete description means that you can do things. You can render more objects into this. You can have decals that, for example, change the normals without changing albedo for just the portion of the geometry that they're laid over. So it's nice because it affords you sort of this easy composability between different portions of your render. It is less nice because, you know, it's like some things are difficult to do there. Materials are, or BRDFs are more painful to do there. This is actually, so when I said that we are gonna try to do this, so we are gonna have normal, instead of 3 10-bit values, we're gonna have 10 plus 10 oct. And then here we'll also have 10-bit, basically roughness plus specular. I think it's just going to be roughness for now. We don't even use this. And then we'll figure it out. But then we'll have these other 2 bits. And maybe we can encode the BRDF ID there. And that's going to be 4 BRDFs, which is better than 1. So you have to play tricks when you go gbuffer, because this single representation of a pixel constrains you. But it also unlocks other things that you can do with that. So overall, it's not too bad. Anyway, so that's kind of it. Let's actually write some code. So I should say, let's actually look at the gloss data, because I haven't even done this. I think it should be in our materials. I don't know what it's called, specular texture perhaps. And again, usually when you, like I was a little bit disappointed by the fact that this scene has spec gloss workflow, because I think the industry has moved on from spec gloss a while back, but we'll just fudge the values somehow. Usually you'd have like roughness and metalness, which is just 2 channels, and then you might have other data, it depends. But we'll just work with what we have. So I kind of want to look at the gloss data, because I want to pack, our shading function doesn't use it, so in theory we don't have to worry about this, but I kind of just want to pack everything that we have. Yeah, so this is this, hold on. We're using alpha testing. Okay, that's fine. Let's do this. Let's look at the RGB data. Which is the specular color, and then we'll look at the gloss factor separately. Interesting. Okay, that's fine. So yeah. Oh, actually, this is good. This is good. So when you look at the specular, what you actually see is that a lot of the specular here is black and white, like it's a shade of gray basically. But then you have some things, for example, you see these handles, they're probably made of brass or something like this. And then you have these, whatever they're called, oh god, English is hard. Anyway, like some other elements of the scene that are colored, where the specular is colored. This actually tells us, so the way metallic roughness model works is that the specular response is grayscale for non-metals and non-grayscale for metals. And it's actually what we see here. So I think essentially we can sort of convert our scene from specular gloss workflow to metallic workflow, kind of on the fly with maybe some loss of fidelity. It's going to be hard to see any of these differences. We don't even do specular at the moment. We don't have a camera that can be moved, so we can't fly to these handles and look at how beautiful they look like in sunlight reflections. Also, I'm not sure why these handles have white specular, but these have yellow. Like, are these plastic and these are brass? Like, that's weird. Oh, maybe these are... anyway, doesn't really matter. So now let's look at the alpha channel. Okay. Is this 7 right? It's so odd that I'm using BCS7 textures. The reason why this is strange is usually you'd expect... Oh, maybe it's gloss versus roughness. Anyway, I'm not super happy with... Oh, no. Anyway, I'm not sure why these things are the way they are. We'll figure it out later when we do materials in earnest. For now, I just want to plug the data and have like a basic shading that's like somewhat representative of what we will want in the future. But we have this data, so we will be able to use it. So that's cool. Do we need to do any more prep work? No. No. Oh, one final thing I want to do before actually converting to ray tracing is I want to have, right now when you enable ray tracing, the cost of the render passes increases. With the new setup, the cost of the render passes should stay constant, but the like this last compute shader will be very expensive, and we don't even have a timer around it. So I want to change this to actually time this last compute call that happens. At some point we will rework the way we integrate the timers is like very sketch, because it relies on like hard-coded indices which are getting harder and harder to manage. So at some point we will refactor this, but I think so 14, 15, how many queries do we have in the pool? Let's see. Oh, we have like a lot of queries. Okay, so 14, 15 is, oh my god. Wait, okay. So I think we can just use, so this is the code that does this final compute call that just blitz from the texture to the swap chain. And this is where the actual ray tracing stuff will go. So yeah, let's do 2 more timer queries, 16 and 17 for the compute. And then let's see. Oh, we don't even process, yeah, because I hacked it in some point. Okay, let's fix this up a little bit, because I want to have complete and correct timing results as we are working on this code without having to like profile them in the run them in the profiler. So we actually have 3 GPU passes. So 8, 9, 10, 11. Why are things the way they are? Is this correct? Oh, because we changed the indexing. Oh my god, this is so weird. All right, so that's fine. So 15 and 14 should be the extra render pass that we added that I forgot to add the timer for. And then there's one more calling stage, which is 8, 9, 10, 11. So 13, 12, 15, 14, and then this is like the sign that you have code to refactor. I just don't want to do this right now. Let's do, yeah, let's call this final or something like this. Okay, and then we have too much stuff. One thing that we will do, maybe I'll do this off stream, we'll see, is like integrating GUI to stop this madness of like displaying text through the title bar. But for now, let's just do this. Okay, so then we have calling time, which is call late, call post. So then we have render time. And I talked about why we have this separate, we have 3 passes now, we used to have 2. I talked about why in, I don't remember when, maybe in the bindless pass, in the bindless stream, maybe in the ray tracing stream. So you'll have to rewatch this if you are confused. I think this is right. Let's see. Okay, yeah, this looks correct. So we now basically just accumulate, because we have 3 passes, each pass does calling and rendering, and then we also have this pyramid building between them, between like 2 of them. So I just accumulated that timer. So now with ray tracing enabled, we spend like 20 milliseconds or something on the aggregate calling stages, and then like pyramid is very quick, and then render takes like 7 milliseconds, and then the final pass, this final compute shader right now, also takes like 20 microseconds. This is because it doesn't do much, it's just a copy. Things will change dramatically. And then if we disable ray tracing, which this shader still has ray tracing code here, but it's just a branch to not cast a ray, then things are way faster. It's like, help me budget this. 6 extra milliseconds for ray tracing on this resolution. Anyway, so that's good, because now the goal is essentially this. So let's compile ray tracing out of the shader. So this is the fragment shader, and using whatever this default resolution is, our total time is 0.37 milliseconds. Let's disable vsync just to confirm. 0.36, 37, whatever. So now hopefully when we implement the G buffer by rendering into this extra texture, the time doesn't increase too much, but then we will be able to replace the compute shader with the shader that actually does ray tracing, and the results are going to be faster than like 7 milliseconds or whatever. So let's just write things down so that we, we'll ignore RADV for a moment, just use the official driver. We'll come back to RADV if we have time today. So let me just write this down. So right now our total GPU time is 0.36 milliseconds without ray tracing. Out of this is 0.28 is render, which is the part that's going to be more expensive with the G buffer. And then the final is 0.02, which is going to be more expensive, obviously. And then once we enable ray tracing, we have the total time changes to 6.9, let's say. And then the render out of this is basically 6.8. And then the final pass is still 0.02 because it still does the same work. So these numbers are going to change, and we will see how much they change. But this is what they are right now with whatever the default resolution is in our scene. Okay. So to work on ray trace on deferred, we are going to switch to debug because that enables validation. And then we are going to enable sync validation because that enables even more validation because we're going to be changing the pipeline or the pipeline setup and the target setup and stuff like this. And it will help to have validation to make sure things are correct. All right, so all we need to do really, this should be fairly straightforward, except that I'm sure I'm going to be confused about some math things because it's been a while. So instead of having a single target for our color render, we are going to have more than a single one. So let's call it gbuffer targets, and then again for now it's just going to be 2. And then whenever we have, let's do depth target. Whenever we work with color target, we now have to work with all of them. I guess here we can do for image buffer targets, if image destroy image device. Depth pyramid. So then when we create them, we'll have to create, should we have a separate format thing? One moment. There's this rendering info thingy. Aha, we have this format, and right now it's the same as swap chain formats. Okay, so so we have to do 2 things, or like 3 things. We have to create multiple targets instead of just creating one. We have to tell when we create the pipeline state that we have more than one. And then when we begin the render pass, we have to do more than one. I'm just going to do these in like random order. So here, let's just have, let's call this gbuffer info. instead of rendering info, just so that it's more precise. So then we are going to have two formats for now. So one is going to be the K format RAG8B8, like this guy. And then the other one is, as I was saying, we're going to have R10G. Format clearly does not exist. Oh, it's like packed. Hold on. R10G. Oh, yeah. Okay, wait. It's like the names of Vulkan enums are weird. Oh, is this? No, this is correct. I don't know why this one is reversed. There's like some formats that are mandatory, more or less, and some aren't. I actually don't remember which one this is, but okay, this is fine. Let's actually do this like this. gbuffer, I don't know, count is a little weird. Size is also a little weird. Let's just do count. And then, so we might have to change this to 3 in the future, and it would be unfortunate if we have to like rewrite a lot of code again. So let's just abstract things a little bit. So now here we have gbuffer for count. All right, now here we have okay. Gbuffer formats I, attachment, sampled, so that is fine. All right, so then let's see where else we use this. Yeah, so this is the place where we start rendering to the gbuffer. Oh, the clear colors are gonna be sketch. It's fine for now. So I guess we will have, oh wait. All right. With just 2, like I could just fill, you know, I could just have like 2 copies of the structs or something like this, but because we might have to have 3, I will just do things the hard way. We just have a loop. Obviously all of this is like very simple, and like I will not, I don't feel pressured to explain what I'm doing much right now, because it's just like very self-explanatory, and it's like a little Vulkan related, but not so much that the code is difficult to understand. All right, so this is where we render. So the barriers are annoying because I have these arrays. I guess the way we will do this is this. For all of the gbuffers, it's a little bit redundant. It's not technically redundant, but it's a little bit silly, because we'll just render to all of these textures at once, but whenever we have a barrier between 2 stages where we want to enforce some amount of synchronization, we have to sort of have a barrier for each one. and we batch all of the barriers in a single call. So things are a little bit, things get a little bit annoying to like spell out, but it's not too bad. So this is the barrier like before we begin rendering to the G buffer, and this is the barrier when we end rendering to the G buffer, and then the next call is like a compute call. So same thing here, I1 plus G buffer count, and then just fill these guys. Yeah. Okay, what else? This is the blit call. So I want to preserve this path where we just have the color, which happens to be albedo, which is fine, like the unshaded color, I guess, in this case, where we only render that into without like any complicated shading. So for this, we'll just render the first one. And in fact, in the future, if we want to, we can bind some hotkey to display one of the channels of the G buffer, which is going to be maybe useful. It's a little weird with alpha. Maybe we'll have to have some custom code for this. So we'll see how that works. G buffer targets. Okay. For now, we will ignore the extra debugging that we might want to have. We have render doc if we need to debug something. Okay, so I fixed the rendering code and I fixed the target management code. Now the final thing that has to happen is the pipeline creation. And then hopefully validation layers tell us what we forgot to do. Oh, and we have to change the shader to like output more than one color, obviously. Oh, I renamed this guy to gbuffer info, so that has to change. Okay, so when we create the graphics pipeline, we have this rendering info that we specify. This is all good, but the one thing here is that when we specify blending, we have to specify for every target that we have to write to all 4 components. I'm actually wondering if there's a way to shortcut this somehow and just not like specify. It's ignored for dynamic stuff. Blend state for each attachment. And I'm guessing this has to match. I'm honestly just kind of lazy and I don't want to. What happens if I just set 0? I wonder. Let's look at fragment output interfaces, this other thing. Yeah, it has to be equal to the color. Okay, that's fine. So basically, we just have to specify for every target that we don't want blending, at least for now, and we want to write to all 4 components, which is a little bit reductive, but it's fine. Let's just have an array of like 8 elements, because it seems unlikely that we'll ever want to do more than 8 targets. We'll assert that rendering info attachment count is less than or equal to, oh, do we have like a count of macro? Oh, we do. Cool. So this is fine, and then like as I'm saying, it's kind of a little bit redundant to have to specify all of this because we don't actually use blending at all, but it's not too bad, I guess. And the validation, not just validation, like the spec wants us to specify both the rendering info color attachment count via this thing and also the blend state color attachment count with this thing. which is fine. Okay, I'm not sure if, oh, I haven't changed the fragment shader, but like it's fine, we'll see what happens. All right, so we have a validation error. Huh. Oh, did I either... No, this should be fine. Oh, oh, no, this is correct. And then the bleed bearers. Interesting. Okay. It's telling us that the barrier, the image on the barrier is null, which is a little bit confusing. But let's see which barrier this is coming from and what the data is at this point. I must have forgotten to do something. And the other thing is the shader doesn't actually write all components. So in theory, should we have gotten a validation error? It's odd that we didn't have a validation error that said that essentially the shader doesn't fully write to all of the attachments that your pipeline state specifies, but maybe this will happen and we haven't hit it yet. Let's see. Yep. That's basically what I said. Oh, the webcam lost focus. Is that still the case? It's hard to see because there is like glare. There is a lot of sun coming through. Right. Not sure if that'll help at all. Yeah. It's fine. My face is not the most important thing on the stream. Okay. So we are looking here. Okay. Interesting. Is gbuffer targets just not like created? No, this is fine. Is depth target not created? Oh, well, that is awkward. Did I remove depth target creation? Oops. Oops. That should not have happened. This guy. Oh, I don't know why. I'm still getting used to, oops. My editor has too much functionality. So I'm still getting used to I should have been able to just do this from here, right? Yeah. Okay, all right. So that should still be here, obviously. All right, let's try that again. So now I am expecting to get a validation error saying that your shader doesn't write to all color outputs. Somehow I'm not getting this error. That is odd. I mean, it's fine, I guess. It's kind of weird. Huh. Maybe it is valid and maybe the writes just get skipped. It's still confusing. But okay, that's fine. So in theory, we now are rendering to all of the color outputs. And in theory, we can now change the fragment shader to split the writes. So instead of just having an output color, we will have, let's just call this gbuffer. And there's going to be 2 colors. And we're going to rewrite some of this shader code, like if stuff works. So whenever we have output color, I guess let's just do this first. I promised a different format. Let's do this. So to simplify this, for a moment, we will ignore the gloss because like we aren't even using it. So let's just do albedo and normal, and then we'll pack emissive into the alpha channel. In fact, because we only support the monochromatic emissive, or because I said we will only support monochromatic emissive, let's just do this for now. And then we will not need all of the ray tracing and endotel stuff. And then we'll switch out the normal pack in a little bit so that we can do the gloss stuff later. But let's start with very, very simple, because I want to first migrate all of this code to the compute shader. Okay, so now the actual color that we have is the albedo color, right? We have lost all of the shading, but the normal, the second channel, should have enough data for us to be able to recover this. And in fact, if I go to the blitz stage where we have this one compute shader, and here, if I render the first image target instead of the second one, the second one instead of the first one, in theory, I should just have the normal now. Okay, so we're kind of done. Not done, but we have successfully filled the G buffer, presumably. We can actually now look at the cost of the G buffer fill in theory, but let's do this first. So now what I want to do is I want to have the compute shader actually read the two buffers that we have written instead of just one, and then compute something interesting, including ray tracing. To do that, we could just change the one that we have, like this shader, but I want to have a second shader so that we can dynamically switch between this one and the full shader based on some like hotkey. And so let's do that, and then we will be able to move all of the computations from the fragment shader back to to the compute shader and restore back the actual shading that we are doing. And then we can like remove ray tracing code from the fragment shader and do some cleanup and measure performance and stuff like this. So basically yeah. All right, so let's copy this to, let's call this shade. And then I think I have to rerun CMake because it relies on my globs to pick up the shaders. So let's leave the source code the same for now. And that's, oh, actually let's, oh, I wonder if I can do an array here. I don't know if my SpearV setup like will work with that or not. Interesting. Okay, so let's just hack this shader to have a different behavior for now. And now we can, and because I want to always have ray tracing here, I guess I will only do this if ray tracing is supported. So we are finally basically getting back to being able to simultaneously have the ray tracing code run when it's supported, and like, well, we're gonna have this unfortunate thing where, in theory, if ray tracing is not supported by the hardware at all, we are gonna use the blitz shader to just render albedo. We could do the full rate of the full shading without the shadows. But because of how complicated things are going to be with the shading in the future, I think we'll just declare that this is fine. And if you don't have ray tracing, then you're just going to have a single color, which is fine. It's going to be a little like uninteresting especially if you go back to the kitten scene, because it's just going to be a single color. But I think for now this is fine. we can revise this in the future if we need to. Okay, so blitz goes to shade. We'll have to pass more data to the shader in the future. For now, this is probably fine. So now here, and the descriptor setup is going to be a little different. And this stuff is going to be a little different. Let's just do an if around this entire block. I have like shadows enabled or something like this. Yeah, okay. Because again, like in the future, a lot of the further work on this render is going to be in like this one block where the actual shading will go. Even though right now it's just a single compute shader with fairly primitive sort of work. Yeah, actually. In the future, this is where the denoising stuff will go. This is where we'll have like a bunch of different passes in compute, probably doing a bunch of different things. So this is where things are going to be more complicated than they are right now. And yeah, so I'm wondering what happens if I pass two things. So I will need at least, well, at most, I will need both G buffers as an input to the shading shader, and I will also need the depth target because we haven't talked about the position at all. But to be able to cast array, we need the position to cast array from. The position can be recovered from the depth value. And so we will need the depth descriptor. All right, instead of shadows enabled, let's call this shading enabled, because that makes more sense now. Okay. I'm not sure if I forgot to do anything. The shader should still work in theory. Let's see. Okay. Perfect. So now this is running our compute shader that has this extra multiply by 2. This is running the compute shader that's just blitzing. And the shader that multiplies by 2. Oh, and we forgot to destroy stuff as usual. At some point, we might want to do some refactoring of some of this code because some of these, with a little bit of work, we could do every incremental step of adding more stuff to the renderer easier. Shade. But I don't want to do this yet. Like, it's not too painful. My threshold of pain of extending this code hasn't been crossed yet, so this is fine. What else did I forget to destroy? Oh, there's the shader module, of course. But yeah, like the shader modules, for example, I might just rework the code to not use them because I think they're optional now in Vulkan. So some of this refactoring may be less mechanical than it could be. Okay, so let's see if we actually have access to all of the data in the shader. I think we might be missing some barriers or something like this. So this is the, I guess this is the gbuffer image. So this is the full kind of setup that I need inside the shader. Well, I also need the acceleration structure, but this is ray tracing related. Let's do the non-ray tracing parts first. I'm not sure if this will work. Let's see. So let's say that instead of the color, yeah. I don't want to spend time on this right now. Let's just not use arrays here. my Spearfish parsing code needs like some extensions probably. It's fine. There's never a case where you want to index this array dynamically, so it doesn't really matter. Okay, so we clearly have access to the color data of both the gbuffer slices. Let's see. This is going to be hard to see probably because the values here are weird in the depth buffer. Yeah, okay, and this is the barrier that we are missing. So when we, it's like here, right? Yeah, we need a more, oh, we were on transition. Okay, we were transitioning the gbuffer images from we are rendering to it mode to we want to read from it in the compute shader mode, but we were never transitioning the depth image because we never like needed to. We now need to. So I guess let's do this and let's just add the depth image here. We could, the other way to do some of this, the other way to write some of this code would be to include the depth buffer into the gbuffer targets because it's kind of part of the depth buffer. But, oops, what? Oh, it's like post depth, post raster. There's some ridiculous stage name for this that I can never remember. Late fragment tests, I guess, is where depth is written, which is a bad name, but I guess that's what it is. Okay, so we are going from late fragment to shader read only, and I think there's an aspect depth that we have to specify. Okay, so I think with this we should be able to read depth. Yeah, so as I said, it's like hard to know, is this value right? Who knows? Let's do this. It's still gonna be off. I just want to make sure that like the data is coming through. Well, great. Okay, fine. I forget what this linear is. It might be 0.5, 0.1. We're gonna actually flesh out the shader to be able to do like depth reconstruction. Oh, okay. Actually, wait, this worked, right? So there was a small bit of the image now that is closer to whatever this value ends up being. Yeah, so here you can see that the depth date is clearly coming through. Okay, so we have the framework, so to speak, right, for the deferred shading fully set up. We're missing two things. We're missing the actual shading and we're missing the ray tracing. So the actual shading is, or should be, fairly straightforward. So let me move this here without like actually enabling this, because we will not need that there. So this is where our TLAS will go. Okay. We are gonna need, oh, we don't actually even need, yeah, this is fine. So that is fine. So yeah, so we can actually now move the code that does the actual shading, which is just n.l if you don't do ray tracing, to the shader. And then we'll deal with specular gloss stuff later. So So the normal is now encoded in gbuffer1 or gb. It's like converted from -1,1 to 0,1, so we have to convert it back. So in theory, if we multiply, if we do a dot with the sun direction, which we don't have yet, so we'll add this. Oh. I should actually have a struct, because this is going to get annoying without a struct. Okay. And we'll need some direction for the ray tracing as well, but for ray tracing we also will need to reconstruct the depth, the position, so we'll cover this in a second. So shade data, we do end.l, and then we had this beautiful code here somewhere, yeah, this guy. And so again, assuming for now, emissive is grayscale, we just need albedo times some shady math. We don't need alpha. In fact, this is a vec3. And then here we'll just unpack. So albedo is just gbuffer 0 RGB. And then emissive, I guess we don't need, that's fine. Okay, so emissive is just the last component. Again, it's like grayscale for now. And we'll have to figure it out. Emissive shouldn't even be from 0 to 1. Emissive should be, it should be possible for emissive to be higher than 1. So it's possible it will need more precision than 8-bit. But we can store it in like some space with some limited range to trade off precision versus quality. There's a bunch of options here. In fact, maybe this should, maybe emissive, I don't know. There's a bunch of ways to pack the gbuffer. We shouldn't really care too much about this for now. So normal is gbuffer1 or gb encoded. And then the alpha is a 2-bit value that we are not going to use now. Okay, so that is good. And then here we'll have shade data like somewhere here. Oh, I wonder why I did this as a struct and the other thing as a vec4. It's a little inconsistent. Okay. So this is good. And then here we'll have shade data. This guy is just the swap chain size. And then sun direction should be like a local variable here. All right, I think this is basically it. I should switch back to release mode, so things. Okay, cool. So this looks about correct. We don't have the exact like old image. This is without ray tracing. Obviously, we don't have this yet, or we haven't plugged it in yet. But this looks about correct. Like you see, end.l seems to work fine. So this is deferred shading. We're kind of done, except that we need ray tracing, and for ray tracing we need the position, and so we need to reconstruct the position from depth. Let me go back to the release mode. One, I just want the scene to load faster. Two, I want to look at, without ray tracing, we had the performance numbers written down without using the deferred shading. So I'm hoping that the new numbers are close to that, but I want to know what they are to actually know, are we losing a lot of performance because we are doing shading separately or not? Probably not, but so vsync is off, disable validation, run things again. Okay, so yeah, it's almost okay. Like it's slightly slower, but it's not too much slower. So we are now at 0.38, where the rendering part specifically is like 0.29 and 0.30. It looks like it fluctuates. Let's call it 0.30, and then 0.02. So the final pass. So that's pretty good. Okay, so the final pass, let me switch back to the whiteboard. Okay, so this was with, I guess, forward shading, shading to the extent that there was shading, right? And this is with deferred shading, again, to the extent that there is shading. You can see we lost a little bit of performance, right? We went from 0.28 to 0.30 render time for the pass, so that's like a 0.02 overhead on the entire frame. And as I was mentioning, it's kind of to be expected because we are now saving more data to memory than we used to for every fragment invocation. Now, again, with complicated shading, you expect to recoup this cost. Our shading without the ray tracing is very, very simple. It's just like a dot product and like a couple multiply adds, right? So it makes sense that we lost a little bit of performance. I am relieved that we didn't lose too much performance because this means that it's like, it's not too bad. Of course, the situation could be different on different GPUs. On weaker GPUs, you could lose more performance because they might have less sort of available bandwidth in relation to the compute, but it's not too bad. The key thing we are looking forward to is implementing ray tracing and seeing this number be hopefully much better. Let's test, let's see if this is actually the case. So I think the only thing I need is basically just reconstruct the depth, the position, right? Yeah, I think so. Okay, so there's a bunch of ways to do the position reconstruction. I will use the dumbest possible way or the simplest possible way, depending on how you want to go about this, because there's like, I seem to remember, it used to matter a little bit how you reconstruct this from the performance perspective, but like performance shouldn't concern us too much because the ray tracing cost will dominate. And there might be precision. So, okay, like reconstructing position from depth isn't like there's more than one ways to do this. And they're a little bit different numerically, even if they are the same algebraically. But numerical behavior is like important because that's what you actually observe. However, I am going to ignore all of the possibly better ways to do this. And I'm just going to say that we're going to take the pixel that we are shading right now. We are going to construct the position of this pixel in clip space, given that we know what the depth value is. And then we're going to just multiply it by the view projection matrix and like do homogeneous divide and hope it works. Because if it doesn't work, this stuff is super painful to debug. Because like when you are dealing with 3D transforms, at least you can conceptualize like the space easily. Homogeneous transforms are more awkward to think about. But so like I'm pretty sure this is going to be more computation that we strictly speaking need to do. We have a reverse Z that's like simplifies the depth inverse and stuff like this, but I really don't want to deal with the math that is possible to get wrong, and this should be the math that's easiest to get right, hopefully. So what we need to do is we need to construct, and we might need this position in the future, so this is very wrong. So we'll have let's see. Yeah, so we'll just write most of this code outside of the ray tracing stuff, and then the compiler should optimize stuff that we don't need actually. So we need the clip space position. The clip space position is basically the x and y coordinates of the clip space position are basically this value which we are using to sample from the texture, except that it's from -1 to 1. And the y is inverse, because of course it is. So that's what it should be here. Now this should just be depth, and this should just be 1, I think. So then, can I do like W? I'll do this. And then you have to do the homogeneous divide, which kind of implicitly recovers the correct depth value and stuff like that. Or like, anyway, I don't want to explain the math. But if you look at this code, if you think about what happens to the vertex when it goes through the rasterization pipeline, what actually happens is you take the world position, then you multiply the world position by the view projection, except like the other way around, I guess. I need to check what the multiplication order is for us in our renderer, and then you do the homogeneous divide. And this is the inverse steps, and the way the homogeneous transforms work should make the inverse math be correct. All right, so then I'm just gonna ignore the shadows enabled boolean for now, because we just swap out the entire shader. W pause sun direction, this is shade data, and then we have to pass TLS and stuff like this, which we are not doing yet. But otherwise this should be correct, I think. I don't know, we'll find out. So, before we go too far, let me double check the matrix order. Yeah, okay, the matrix order should be correct. Okay, so this is the part that will be the most painful to debug, so I'm hoping it just works. Because there is like matrix transposes and stuff like this, and do we have the view projection matrix somewhere? We do not. Do we have the view matrix somewhere? We do. Okay. So I mean, in theory, this is just inverse. It should be projection times view. The name view projection is a little bit unfortunate because it's not quite correct given our matrix multiplication order. Because what should happen is like projection times view times world position is the order to transform the world position to clip space. And so the matrix is projection times view, and so the inverse of this should hopefully do the right thing. Anyway, hopefully this just works. If it doesn't, we'll find out. We could, ignoring the ray tracing stuff, we could render the world position just like as a debug. The problem is it's, again, difficult to visualize the world position in a way that makes sense. It's not between 0 and 1, etc. So I think I'm inclined to just try to go for ray tracing like directly, and then maybe it works. And then if it works, then we are set. And if it doesn't work, we'll figure out how we debug this. So I have to pass the TLAS structure as an extra descriptor, and in fact I don't need it in the fragment shader anymore. Oh yeah. I am gonna remove this separately, or actually yeah, that's fine. Let's do cleanup separately. So passing the TLAS shouldn't be the only thing required. Yeah, I think we are just ready to try this. I don't think anything else should be necessary here. Oh, hey. 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 Okay. All right. See, the most straightforward way to do a transform is to think about the matrix form and then just inverse things and then, see what happens. All right. So, the performance. Okay. So, let's. So hopefully it's relatively clear as to what happened here. Except if you have done deferred shading, you know what happened, and if you haven't done it, you are confused because this math takes some time to think about. If people have questions, I may explain this more. Okay, so what happened now is that we have reconstructed our entire pipeline. I'm going to leave this defined so that in the future we can toggle it on and off if we need to do performance testing and stuff. But we have reconstructed the pipeline with deferred shading, with ray tracing, which should mean now that we are doing the absolute minimum amount of work possible, because for every pixel, well, for every pixel that has actual geometry in it, in theory, there could be pixels that refer to the sky. We don't have pixels like this on this image, right? But there could be some pixels that effectively have depth of 1 or whatever we clear it, maybe 0, whatever the clear value is. And for these pixels, we technically shouldn't really do ray tracing. We shouldn't even shade them at all. But other than this, we are doing the absolute minimal possible amount of work to actually do the ray tracing. If you look at the performance numbers, so the total frame is 1.54. And then if you look at the render time, it's still the same. Obviously, it's like between 0.29 and 0.30. This is expected because we haven't changed that at all. We already measured this in the gbuffer thing. And then the final blit pass is 1.18 milliseconds. So as I said, like this is going to be where the time is actually going, right? Because this is the thing that is doing the ray tracing. And then in full screen, the timings are different, but like we don't care about the full screen yet. So you can see that we are way better now than we used to be from the performance perspective. What is this, like a 4x? Yeah, so it's about a 4x improvement in total frame performance by moving the calculation from the fragment shader to the compute shader. And again, it's not because compute shaders are somehow magically more efficient than fragment shader. It's because of the inefficiencies in the rasterization pipeline meant that we are executing way more fragment shaders than we are now executing compute threads, because we could be running more than one per pixel. And some of them we could fix in other ways that are not deferred shading, but some of them are very difficult to fix in ways that are not deferred shading, so we just went full deferred shading. Cool. 1.54 milliseconds. So this is not 4K, right? This is whatever the resolution this is. This is like 1536 times 1152, so it's about a 1080p, slightly more. Oh, slightly... it's slightly less, I guess, pixels, slightly fewer pixels. It's fine. At 4K, we have 4.25 milliseconds, which is pretty decent. If we had 3 to 4 rays per pixel, we could probably hit 60 FPS. Because this is 4K, probably the most efficient way to do this would be to render fewer than 1 per pixel rays, to trace fewer than 1 per pixel rays, and then do a denoising and stuff like this. But this, we will definitely not do today. Okay, cool. So I'm pretty happy without this. I think I'm going to commit this code. Oh, I think I'm going to remove like stuff we don't need anymore from the fragment shader, commit this code, look at questions if they exist in chat, and then I'm going to talk a little bit about the performance on AMD with ray tracing specifically. All right. The previous 2 streams were like 4+ hours. This stream will not be 4+ hours because the previous 2 streams I wanted to get done before I left, and now that I'm back, I don't feel the need to rush things as much. So we will, it's been under 2 hours. I think it's going to be like a 2.5 to 3 hour stream probably today. Okay. Yeah, I haven't dealt with gloss at all and specular and stuff like this. This ideally should happen when we do metallic for real. Maybe I'll do normal packing differently, and I'm not sure. I think for now this is actually fine. So again, the longer term, like the gbuffer format is nowhere near close to final. There's at least two things we need to think about. Emissive should be not in a separate buffer, but like emissive encoding should somehow support albedo relative and higher, like colored and HDR emissive with some constraints. Like it's a waste to do a full, you know, emissive, like what is it, like 48-bit emissive. It's a waste to spend 48 bits on emissive. But the way we implemented it right now is it can't be too bright, which is a problem, maybe. And it can't be colored, which is a problem. Now, is it the problem in our scene? I don't think so. Is it a problem in general? Yeah, probably. So ideally, this should be fixed. And then specular glossiness encoding is missing, or rather, we should encode roughness plus metalness somehow in gbuffer1z and use oct encoding for normal. And again, probably it's unrealistic to expect probably that just 2 color channels in gbuffer are enough. 3 channels are probably going to be enough, depending on how we manage to pack things in the future. 2, I don't think will survive for very long, but for now, let's just keep using 2. Because again, until we do complex material shading, like these issues are not going to be super important. Until we do any specular, like this doesn't matter because we just need the normal for NZL. All right, I think I already removed the ray tracing thing from this. There's this giant gap here. Oh, this is relating to task shaders. Yeah, we still support task shader execution mode, which is why this one is like binding 7 or 8, and the last one we use here is 1, because we need like a bunch of data to bind to the task shader if it's present. I am gonna remove this at some point. I'm not sure when, but probably not on stream because it's a waste of a stream to just clean it up. So okay, so I removed class from here. I can remove this from here. So it's still here, which is correct. And then there's probably stuff in the global structure we don't really need because it has this stuff which should never be used, I don't think. So, oh, maybe I should move. Nah, I'm gonna leave this as this. So yes, I think these guys should not be used. And this is only used in task shader, but that's a cleanup for another day. So let's see if that's correct. And again, in addition to the performance benefits, this decoupling is nice from the structuring your code perspective. So now the render passes don't care at all about anything shading related. They just care about how do we need to call the meshes, and then how do we need to project them on screen, and that's it. And then there's the view matrix like inside call data somewhere. I'm gonna like refactor some of this in the future, which is just nice from the purity perspective as well. Of course, if purity was the only thing we'd gain from this, then we wouldn't ever do this because it's more bandwidth. So, but we also gain a lot of performance from it. Okay, so let me check that 3 modes work. I think that's the entire cleanup actually. So that works, that works, that works. And again, maybe it could be worth it to do visualization for debugging for this and for this data in the future. But for now, let's just keep it like this. Should I do any more cleanup? I think that's it. Let me submit this and then I'll look in chat and stuff. Okay, so let's turn resync back on. Shadows, shading, shade data, gbuffer count. As you can see, the diff is like very minimal. This is very pleasant. One thing I should have mentioned about transparent objects is this is not that much code. So in theory, we could maintain like both pipelines. In theory, we could do the shading pass to the gbuffer and then render transparent objects to it on top with the fragment shader doing the ray tracing, right? So in theory, we haven't actually lost the ability to do transparent objects as a separate pass. Or like we kind of lost it, we never had it, but it's easy enough to gain back, right? Like it's not a big deal. Now, why is this reformatted? Oh, okay, I see. Now, I don't want to do it this way because of the depth ordering issues and performance issues that I mentioned. But if we have to do it this way, we can, right? So I'd rather find a more unified solution that's like reasonable performance and reasonable quality and good behavior. But if we have to do translucent objects, I should say not transparent objects, in the future with a fragment shader and eat the cost of ray tracing of this, we can. Nothing, that ability has not been lost. We'll just have to write a little bit more code on top. And again, if we want to do visibility buffer in the future, again, we can. Visibility buffer would essentially mean that instead of doing the gbuffer rendering, we're just ignoring all of the texture fetching in the fragment shader, just render the triangle ID. But then in the shading compute shader, we actually index the triangle, figure out what the material of the triangle should be, figure out what the textures are, fetch these, etc. It's all possible. We have bindless now, so we can all just bind the giant array of textures that we have to this compute shader and just index through them randomly. Like, it's not a problem. It's just that it's more code. It may affect the data layout and stuff like this for some of the geometry buffers. I just don't really want to do it. And with meshlets in particular, it's interesting because it's like, you wrote the triangle ID, where do you get the triangle data from? There's other ways to do this that don't rely as much on the triangle IDs. There's a bunch of ways to do all of this. For now, I think deferred shading is the simplest thing to stick with for us. But, so this is day 25. We will only explore like extra ways to do this stuff if we really have to. Deferred shading plus ray tracing. So to fix the various inefficiencies with rasterization in one fell swoop, we now do gbuffer laydown via rasterization and do the rest of shading in compute, which means we only trace one ray per pixel, regardless of the geometry complexity. Overdraw, quad, it's called like quad overshade usually, not quad overdraw. RenderDoc just like simplifies sort of both terms to make them one visualization, I think. This is way faster, and it allows future improvements by decoupling ray tracing from shading and doing denoising. So like, let's say you wanted to do a denoise of shadows without deferred shading. What you have to do is you have to render the geometry to at least have the position of the ray, or to the position of the pixel, or maybe trace a ray in the fragment shader or something like this. Then you have a buffer, then you denoise that buffer, but then you have to render geometry again, where you incorporate the results of the denoising pass into your shading pipeline. So it's kind of two geometry passes anyhow at that point. And then if you want to do multiple denoising stages, then you might have to do a gbuffer anyway. Like it's all gbuffer by breaking a bunch of stuff like transparent objects. Gbuffer makes a bunch of other stuff like denoising more straightforward to integrate. All right, so I think this is good. Okay, so let me look at chat and then we'll talk about more performance stuff. At what point could someone be able to say no Vulkan? Hey, I don't love the absolute statements like this. Vulkan is a very large API that has a lot of extensions, and besides the API itself, that's very difficult to know because it has so much in it. There is the behavior of this API, which the spec doesn't tell you about, but you actually have to know to write code in Vulkan that performs well. So, for example, the things that we are going to talk about right now are kind of related to Vulkan, sorta, in the sense that there is a Vulkan driver that implements things a certain way, but also kind of unrelated to Vulkan. But knowing them is kind of important if you want to understand the performance of your code. So I don't know. I think the question is essentially poorly formed because you shouldn't have a set of conditions that make you be able to claim that you know Vulkan. But like implementing, the more rendering techniques you implement in Vulkan and the better performance you achieve with them on a given hardware, the closer you are to like understanding. But I don't think there's ever a point that's useful to say, I know Vulkan at. Just like C++, like it's kind of meaningless to say I know C++. I don't really know C++ at this point because like I used to feel like I know C++ well before C++ 11, and at this point I really don't know C++ like 20 or 23 because they have so much stuff that's added there that I just haven't had the time or desire to look into that. Like I just don't know. I know a subset of C++ to a decent degree, and that's it. So does deferred shading have fatal flaws? I would say, so okay, the transparency is the big thing. Deferred shading kind of relies on this single pixel having a fixed set of attributes, right? Like albedo, etc. When you have multiple translucent layers, you kind of lose an ability to talk about this when you're doing deferred shading. In practice, either deferred shading renderers have a forward shading pass after the deferred, so they do opaque geometry with deferred, and then they do transparent geometry after this, or they try to implement some form of order independent transparency with some limitations. For example, you could say, oh, gbuffer is compatible with transparent objects. You just have at most 4 layers of transparent objects, and you just store 4 copies of all of the gbuffer data per pixel, or 5 copies instead of 1. This works. It can't support more than 4 layers. And it's slow because you always allocate, well, it might be fast, sort of, like it's a lot of memory. It could also be slow because you allocate for the worst case. There is more complicated techniques that try to not allocate for worst case that have other pitfalls. So transparency is a weak point, is a significant weak point. And performance is where deferred rendering is complicated. We just had a 4x gain from deferred renderer. If we had the depth 3 pass, it probably would have been a 2x gain, not a 4x gain, but I'm sure it still would have been a gain. We would try this, but I just don't want to spend time on this. But the performance story in other renderers could be worse because you are losing you're trading off the bandwidth, and the more complicated your shading setup is, the more bandwidth you're trading off. So that's not ideal. There's things around deferred shading that people used to say are a problem. For example, an ability to implement multiple BRDFs. I think this is not really an issue at this point. There's many renders that have deferred shading set up with many materials. There is multiple ways to do this. We might go into this when we go more into materials. In fact, we will have to, right? Because like I'm not even sure what the total amount of BRDFs that's useful in our scene is, but if you think about, oh, I want to do anisotropic specular, which is basically objects from metal that tend to be structured a certain way. You want to have a different shape of specular highlight. For this, you want to A, save a tangent per pixel, B, incorporate this into your BRDF. Now you're like, okay, how do I do this? Do I have space to put the tangent in? Do I reconstruct it in some faked way? Do I want to just spend the computational power to do that always versus have this only run for pixels that need it? And then you repeat the set of questions for every new different material type. It has to be a very different material type that's not easily representable with your gbuffer setup. And so from this perspective, deferred is not optimal, because in forward setups, you want new material, oh, you write a new shader, here's the new material. So it's much easier. So like deferred enables a class of rendering techniques that are difficult to achieve in forward, especially around, like I mentioned, denoising, temporal anti-aliasing, stuff like this. All of these techniques kind of break down for similar reasons to deferred in a lot of cases. But it makes some other techniques like translucent rendering with just blending much more difficult to do. It makes multiple materials kind of not as straightforward to do, because you have to think about how to integrate them for every material. And some classical rasterization techniques like multi-sample anti-aliasing become much more expensive with gbuffer, like way more expensive. But people are not using MSA much these days. Some renderers do, some renderers don't, but most AAA games, I think, have moved on from MSA. So it's a complicated like trade-off. I don't think it's the case that using a deferred shading can be a deal breaker in the sense of, oh, we can't ship a game with deferred shading. I think that's unlikely. But there's like a bunch of problems that you have to solve. There's this quote, ray tracing is kind of the same way. There's this quote from somewhere. Oh, I think I was reading Ray Tracing Gems 2 the other day, and they have this quote in the intro that's something like, rasterization has all of these hacky algorithms that require all of these weird workarounds to achieve the picture quality. Behold, hardware ray tracing is now available, and it is the future. You can now forget all of the weird techniques and hacks that you've used in rasterization, and now you have to relearn a lot of new hacks that you have to use in ray tracing to make that work. So that's fun. So that's what we are going to be exploring in the future on these streams. But yeah, I don't think that like it's a deal breaker one way or the other usually, but it can have issues. On mobile, deferred shading can be more problematic just from the performance perspective. But everything on mobile is problematic from a performance perspective. So it's hard to know. I wouldn't make a definite statement one way or the other. For a while, deferred shading was like the rage, and then a lot of renderers have moved to forward plus, it's usually called. But forward plus has a lot of efficiency issues as well. So some renderers are moving back or doing a hybrid setup, etc. Like it's hard. There's not a definite answer to questions like this. Okay, so let's talk about performance more. We now fixed, to the extent that we can, the application side of things from the performance perspective. I'm, again, just ignore 4K. I'm just going to work in whatever this resolution is, just to not have to like maximize the window every time. So we have 1.54 milliseconds per frame right now. And I've written down these numbers, which is good. So let's try to run this again under RADV. I forget every time. It's a ridiculous command line. Okay. Okay, so this is running with RADV. This is now 2.37 milliseconds. Let me write this down. So this is deferred shading plus ray tracing with AMD driver. And this is deferred shading plus ray tracing plus RADV. So 2.37 for the full, I should enable vsync. Okay, you know what, whatever. So the renderer is Oh, interesting. Let me actually enable vsync. My expectation was slightly different. Or disable vsync. I talked about this before, but when I disable vsync, it just allows the card, it just keeps the clocks of the card at like a slightly higher level. Yeah, interesting. Okay, huh. Which usually results in more stable timings and sometimes higher timings, but it's not critical. But like this is why I keep flipping back and forth between vsync on and off. There's other ways to do this that I don't have access to on this system. 1.90, who knows, 7. Whenever we implement ImGUI, which might be off stream, oops, I'm looking forward to solving problems like this once and for all, because you can like draw a graph or something of the final pass performance over time and not deal with this flickering, oh, it's sometimes 2.00 and sometimes 1.97 milliseconds stuff. Okay, so as you can clearly see from my amazingly recognizable handwriting, so this row is the AMG driver, this row is the RADV driver or the unofficial driver. So I forget what it was 23 on 20 in 4K. It was 23 versus 13. So you can see that the render cost is very similar. I'm actually slightly surprised because RADV was a little faster before we did ray tracing. And now it's a little slower with the G-buffer stuff. So it's possible that RADV doesn't have some of the same optimizations for multi-render target. I don't know. This is a little strange because I guess I haven't compared culling. Maybe culling is different. You know what, it doesn't really matter. I'm slightly surprised because I expected that this number would be a little lower, but like it doesn't matter. But this is the compute shader that does the actual shading, and you can see that on RADV, it's again almost twice as slow, right, as the MG official driver. So clearly whatever RADV is doing in terms of implementing the ray tracing is less optimal. Let's do, I already had a trace here, but let's do another trace actually, now that we have all of the ray tracing stuff working better. Oh, should we do a render doc capture? No, I don't think so. So it's just a compute call after these, and this compute call has access to the entire G-buffer. That's it, right? So let's just ignore, and render doc doesn't do ray tracing, so we can't like look at the full frame anyhow. Okay, so let me do a performance capture or not. What? Hold on. What do you mean? Wait. Is it like not compatible with vsync off or something? That is strange. Oh, whoa, what? Okay, that is not even our crash. Hold on. Okay, not sure where this X came from. Okay, so let's do, this is an RGP trace. Oh, let's actually try to get both. Yeah, okay. So what we are gonna attempt to do, I haven't actually tried this before, but what we are gonna attempt to do is to get two RGP traces, one from the RADV driver, which is this one. Let me close the previous one because I'm gonna be endlessly confused. Oh, one moment. Okay, this is the old one. So this is the trace from the RADV driver, which is like twice as slow, right? So this is our compute call, which takes oh, interesting. Oh, I'm glad we did this. Cool. So the times here are lower than what I have written. Like I have 1.97 marked, and this one is 1.5. But if the GPU clocks are different, then this could be why, and they might be different. I don't wanna obsess about the raw numbers too much right now here, but I want to talk a little bit about the mechanics of the implementation of ray tracing and what we might be seeing as a consequence. What is interesting is, though, is this the right? That is confusing. Do we have the right barriers? How is this possible? Maybe the performance is worse because we have some barrier stuff not working correctly. How is this possible? So the thing I'm confused by is this diagram shows what stages are active at what time. This is the last, yeah, this is the pass that like renders geometry. In this last pass, it's like just transparent objects. For some reason, during this region, there's an overlap where the fragment shader, which is the blue thing, does a bunch of work, and the compute shader also does a bunch of work, which shouldn't be possible because the compute shader needs access to the complete G-buffer information written by the previous pass. And this indicates that it like starts before that pass ends, which like either the profiler is lying to us somehow, or it's actually happening and then our rendering results could be incorrect in certain cases. So that's like interesting. The other really fun thing that happens is this segment, which is a substantial, it's like 10% of the entire compute call. We spend in this region that's long, that's not occupying the GPU very well, but still does like a bunch of work here clearly. This might happen if some pixels are much more expensive to shade than other pixels and there's not a lot of them. I already talked briefly about this potential problem when I talked about the quad overshade stuff, and I said deferred shading fully fixes this, but this is not quite true. We dispatch one ray per pixel, guaranteed, but the amount of work that a single ray does is variable because it has to traverse the acceleration structures and do triangle intersections and stuff like this, and the depth at which that traversal happens depends on the complexity of geometry in that region and how it overlaps with like acceleration efficiency. So it is possible that some pixels are way more expensive to shade than others. There's another AMD tool that I haven't tried yet that I probably won't do now because I'm not sure. I might try to do this with an official driver if it just works. There's another AMD tool that might show what like the impact is in this case, but this might mean essentially that there is parts of the scene that are really expensive from ray tracing perspective because the ray goes into some weird part of the BVH that's like expensive to traverse. So let me first look at this. I want to do this capture with the official driver. Oh, actually, let me first do the capture with the official driver, and then we'll see if it shows the same problem. Oh God, okay, hold on. This thing is like a little flaky on Linux. I'm not sure if it'll just work or if I'll need like cursing the driver to make it work. Let me see. I got it to run like before the stream just to see that I could, but I'm not sure what the exact sequence of steps was. Because on Windows you can like launch an executable, I think, from that tool that I just had open, but on... Oh, great. All right, amazing. I think this is gonna kill everything. Oh, somehow things work. Okay, let me, is the stream alive? Okay, I think the stream survived somehow miraculously. Okay, so I will not try this again. I'm not sure what happened. How did this even happen? I'm very confused. Okay. Let me try to do this again. Yeah, of course it's poor. Hold on. Something went weirdly wrong. Okay, so this is fine. Interesting. Why does it still say poor? Okay. The OBS settings are healthy. I don't even know if this is correct. Maybe it hasn't refreshed? That is weird. All right, let's assume YouTube is being weird. Okay, so what just happened is I ran the application with the developer panel open, and I wanted to do an RGP trace, but like the application took like a second to render a frame, or maybe more than a second. But nothing crashed, which is good. So I don't want to repeat this, which is a little annoying because I wanted to look at the capture in RGP. So let's ignore. I won't be able to like compare the RGP traces. Okay, that's fine. I know what I want to talk about anyway, so like that's not too bad. But all right. So getting back to this, let me first quickly double check synchronization because this is bizarre. The thing that RGP is showing me is bizarre, and then we will see. Because like after this render, this barrier should synchronize all of these barriers basically. Yeah. It even does the layout transfer. This part is shocking to me. I don't fully see how it can be wrong. It seems like a thing that the profiler shouldn't be able to lie about. At the same time, it doesn't seem like a thing that should be possible. And like, so if what I was saying about the overlap is true, then we should have flickering issues on the pixels that are rendered by the transparent pass. Except that I don't think we have them. Yeah, like the image is fully stable. I mean, unless I like resize it, obviously, but yeah. Oh wait, this is the official driver. One moment. This is the RADV driver. Nah, I don't trust the profiler right now in that particular segment of the frame. Because if there was an overlap, I would definitely not be seeing correct results on some of these sizes. No, this should be impossible. Let me do another trace actually. Hope it works. Okay. And then maybe I don't, this should not be possible. I don't know how this happened. I guess I could explain this in a different way. Yeah, this is suspicious, people. This should not be. It should not be the behavior. This could be explained by. I could see some cases why maybe. Oh, you know what would be fun? How large is this segment? 41 microseconds. How large is this segment? 52 microseconds. So I think my guess is there's some bug in RGB trace from RADV somehow, because these are two different stages. So maybe I could see how this could happen in theory. So maybe there's a bug in RGB trace that kind of offsets the compute timeline here, like left by a little bit for some reason, whatever, some barriers, I don't know. This would mean that the real picture looks more like this. And so the thing I was saying like 10 minutes ago about the very inefficient rays, it still happens to some extent, like here, but it's less severe than the trace would let you to believe. I would trust RGP more if I did the official driver RGP trace, but for some reason this didn't end very well, and I'm not sure why. I did the RGP trace just fine this morning from the official driver with fragment shader. Okay, you know what? Whatever. Let's talk about the thing I actually wanted to talk about. So, why do we have bad performance on RADV and much better performance on AMDVLK? There was a question in chat about whether RADV uses the hardware accelerated ray tracing units, the RT cores. The answer is yes. The reason why I know this without testing is I tested this at some point a couple weeks ago after I did the original stream. RADV has the debug setting called emulate RT or something like this. I don't remember. It's probably not emulate RT. Let's look at RADV source code. It has some setting to enable software traversal, like software implementation of the ray tracing traversal, of the ray tracing check. The traversal is always software. Yeah, this guy. Oh, I guess it's perf test. Oops, perf test, not debug. Emulate underscore RT perf test. Okay, so you can use an environment variable called RADV perf test, and then set it to emulate underscore RT. Yeah, so you can now see the frame time is 12 milliseconds. The final frame is like 12, the final compute rate is like 12 milliseconds versus 1.97. So in RADV, so like it's 6 times slower. So this is what happens when you don't use hardware instructions. So it is using RT cores. However, there is a couple things that I believe are going on. Because I haven't spent the time rather to compile the official driver, I don't fully know that this is going to be correct, but let's talk about how the ray tracing is implemented on AMD hardware. Let's look at this. Hopefully this is going to be... Yeah, this is just, the hit count is just, oh, no, hold on. All right, okay, never mind, all good, okay. So let me try to show, no, I can't. The hit count is broken here. Okay, so let's just not trust the RGB too much on RADV. It's clearly running into some uncharted territory. But I talked about this a little bit last stream when I was looking at the shader, and I was seeing all of this math in the shader, and I was like confused as to where this math is coming from. Shouldn't RT cores be doing this, stuff like this? I now know because I looked into this, so let me talk about why. I was also hoping to show you guys some specific instructions. Somewhere. Oh, this is actually kind of garbage, by the way. Well, actually, no, this is the... No, this is fine. Okay, I was hoping to show you guys the distribution of time that different steps take in RGP on AMD hardware when using RADV, but I don't know that I should trust any of these numbers right now because the hit counts are 1. And usually, and before when we did this with Fragment Shader, the hit counts were actually reflective of the kind of cost distribution in different stages, and now they aren't. So because of this, because I don't trust the hit counts, I'm not sure I should trust the clocks, etc. Point being, I just don't trust any of this. This all seems sus to me. Let me just double click. The PSO hash ends in 510 and 853. 853 is this one. So this is clearly the right shader, but this is all. Oh, now it shows the hit counts. Oh, okay. Okay, now it shows the hit counts. Interesting. Okay, there's clearly bugs everywhere here. Is this the thing I wanted to show? Maybe not. Actually, maybe. No, this is the global load. One moment. I'm trying to find a specific thing here and failing for some reason. But I'm not an expert on. No, this is the. No, this is scalar loads from the. Okay, never mind. Hold on. Maybe this is what I am looking at. Because what would this load so frequently? Oh, no, this is. I think this might be the thing. Yeah, I think this might be the thing. Maybe, maybe not. All right, anyway. So if you look at the code that RADV uses to implement ray tracing, and I don't want to actually do this, there's like a bunch of code like somewhere here that deals with the what's called lowering of the SPRV into NIR, and then there's separate code that lowers NIR into AMD ISA, which is basically implementing the ray query extension that we're using in hardware. And what this does on AMD hardware, or what this does in RADV, is as follows. Let me go back to the whiteboard. So we talked about this last time, that there is class, like we built these structures last time, right? There is class, which has the objects in it. And then every object has BLAS associated with this, which is the bottom level of structure, which contains triangles, right? So then the object contains a reference to BLAS, which contains triangles. And an object has a transform matrix as well. And it has a bunch of flags for like stuff with respect to how the objects should be filtered when you're doing the query. So what the driver has access to from the hardware perspective on RDNA 2, this is going to be important later because my GPU is an RDNA 3 GPU, is this. It has a single instruction. I have a PDF opened someplace here. I'm not sure where. Where's my PDF? This is an RDNA 3 doc, but it's actually the same as RDNA 2 doc in that section because they haven't updated it. So it has essentially one instruction. There's two instructions, but one just deals with 64-bit pointers and one with 32-bit. They're the same. And this instructions does the following. It loads the BVH data from memory and then performs either array box test or array triangle test, depending on what the node is. So if the node is like a leaf node versus a non-leaf node, it performs the relevant test. And then it returns the result. When it's a triangle node, the result is just, have you hit the triangle or not, what's the intersection point, etc. When it's a branch node that has 4 boxes in it, then you have to do a 4-array box intersection test, and then you have 4 hit points potentially. You sort them by the t value, so by like the first intersection point where the array enters the box, and then you return the result sorted. That's the only thing the instruction does. It has one node that either has boxes or triangles, and then it does a test. Now, how do you implement ray tracing with that? Well, there's the rest of the shader, right? It's like draw the owl. Here's the rest of the owl. So the shader does the following. First, it has to traverse the class to find all of the objects, or to find each object in kind of in lockstep, I guess, that intersects the ray. For this, it has to use that instruction to actually do the queries. So it goes to the first node of class, like the root node. It has 4 children. It does the ray test using that instruction, and then it gets between 0 and 4 intersections back. So then it has to recursively go into each box that has an intersection until it finds the leaf node that has the object in it where the ray succeeds. The first problem here is, how do you do recursion in the shader? There's no way to do function calls in the shader. There's no way to have like a stack in the shader. So the way they do this is, on RDNA 2, is they build the stack in shared memory using manual addressing instructions. I was like hoping to find this here. I don't think this is that. This is like 4 boxes, maybe. I'm not sure where the stuff is. Maybe this is this. I don't wanna. I should have like looked up before the stream. But like somewhere here, there are instructions that do like stack emulation basically on the GPU. So that's like the first thing that you have to emulate, right? And then you have this loop, like the classical. If you ever took a computer science course, very early on they teach you about recursion, and then they say, well, a recursive algorithm can always be converted to an algorithm that is not recursive by emulating the stack. So you have the stack in an array, you have a loop, like while there are items in the array, you get the last item, you maybe push more, stuff like this. This is what they do. The way they manage the stack memory is just some hard-coded maximum depth of the stack that they know is sufficient for any valid tree. And when they access the elements on the stack, they have a pointer, a stack pointer that doesn't exist in hardware, so it's just an index. And then they have to dereference that stack pointer by converting that pointer to the actual memory address in shared memory, and then doing all of this stuff, right? So basically, there is the software stack in shared memory. And because it's in shared memory, it's shared between all invocations of between all threads in a wavefront or in warp, or actually in a unit larger than warp, but like doesn't really matter. And the driver has to generate the code that like indexes all of this stuff correctly. So then with the software stack, we can implement recursion. So then you do the hardware array box intersection. So then you get to the actual object, to this guy. So then you have to trace the array through this object, but the problem is the object has a transform matrix that you have to apply. So then what they do is they have to transform the array in software, so to speak, right, per object hit, software transform of array to object space. This is just a multiplication of the array vector and origin, or the direction origin, by the inverse matrix. They store the inverse matrix in the object, but this is where all of this ALU that I was confused by last time comes from. I think it's like, I don't know, like this stuff. or maybe not. Maybe it's probably like this stuff. It should be a bunch of FMAs and then once you transform the ray direction, you have to normalize it because the object might have scale in it. So this is what that is. It's it should be 2 matrix vector multiplies, probably with this guy, followed by a normalize of the direction plus maybe some more stuff, who knows. So this is what these instructions do. There's not too many of them here, but like this work has to happen. So then we now have the ray in object space, and we now have to trace it through BLAS, which again then goes into you have to then again do all of these software stack operations. To actually traverse the bottom level structure. That's the same as the other traversal. You again have to do hardware array box stuff. And then that's kind of it. And then one final subtlety in the hardware array box code is kind of in both places, I guess. It's mostly on this top level. Is it on? There's 2 subtleties, I guess, in both levels. The first subtlety is after you do hardware array box intersection in the class traversal, you have to here also do the filter by flags. I haven't talked about this filtering in the last stream, but it's things like, oh, I want to only trace through transparent objects, or I want to only trace through opaque objects. There's a bunch of like flags on the wherever we do ray tracing. There's a bunch of flags that you specify when you trace. We actually specify, I added this after the stream, but we actually specify that we want to call the non-opaque objects, as in we want to only trace through opaque objects. This is because for non-opaque objects, we have to do alpha testing, and we haven't done this yet. If you remove this, then you will have like a different behavior. And things like this have to be tested. There's also this call mask that's also tested. There's like stuff that has to be done per object to filter out some rays. And then in the BLAS code, and this is all in software. This is software filter, I think. And then in the BLAS code, with the hardware array box intersection, returns you 4 results when the node is a branch node, because there's 4 boxes that it has to test. These results are sorted, and as I mentioned, it's sorted by T, which is the ray intersection like entry point. So this is the RDNA2, this is the steps that are required on RDNA2 to implement ray tracing. And the only hardware accelerated things are this ray box stuff that I have circled, right? That's the first complication. The second complication is that the hardware only knows that you want to trace the BVH node of a certain structure, but doesn't know how to build it. And so in addition to all of this code, in any driver, there is the BVH builder. And this builder would be different between the 2 drivers, obviously, right? Because it's different code written by different people. And there is a certain set of things that the builder, there is a certain set of decisions around building acceleration structures that the driver could be making differently. Okay, so why am I talking about all of this when the GPU that I have is the RDNA 3 GPU? It's a 7900 series. Well, the RADV code is the same between RDNA 2 and 3. They have an implementation of ray tracing that is using the hardware ray tracing units introduced in RDNA 2. Has anything changed in 3, you might ask? The answer is yes. Unfortunately, I can't. So there's 2 things that we are hitting. There's 2 problems that we are hitting. One is there is RDNA 3 that has some improvements, which I'm going to talk about in a second. And the other one is there is the BVH build that could just be different between the drivers. And both matter for performance. The better your BVH is, for example, the better performance is going to be. And there's a couple of things I want to touch on this, but before this, let's talk about the RDNA 3 part. So what did AMD add in RDNA 3? Unfortunately, or maybe fortunately, I don't know, they didn't add. So if you wanted to look at the NVIDIA picture of this entire thing, NVIDIA doesn't document what it is. I don't know what it is, but my understanding is it's different. Let's just call it like this. But it's like substantially different. But RDNA 3 versus 2 is close, but not exactly the same. And I want to show you a cool trick. I checked that it worked before the stream, so. But let's look at the extra things they have implemented. This is public information. It is available through. There's a bunch of like slides from some presentation that I didn't find a PDF for, where AMD talked about what they have added in ray tracing. They say they have more efficient handling for ray diversions in ray accelerators. This, I believe, is just a built-in hardware unit that we are taken advantage of regardless of what we do. Then they have added dedicated handling of traversal flags. This is the thing that I was talking about where I said, oh, software filtering of flags. In fact, if you look at the RDNA 3 docs, they say somewhere in them, they say pointer flags. There's a bit that says whether you should use pointer flags to enable hardware calling and primitive type-based calling. And I think this is new of RDNA 3. I'm not 100% sure. One complication is this. So this is the RDNA 3 ISA. Unfortunately, it doesn't document some of the additions. And the way you know about these additions is twofold. One is you read these random AMD slides. The other one is you look at the actual real implementation of all of this code in AMD official drivers, which is part of this GPU RT project that you can find on GitHub. It's just open source. And if you, one thing, for example, that you'll find here is there's a bunch of HLSL code here. But one thing that you'll find is, there's two things that you'll find here. This is how I arrived to all of this knowledge. I was reading the source code of GPU-RT to try to understand what does it differently. And they have this thing called RayQuery 2.0 and RayQuery 1.1. I believe this is the version number of their GPU IP or ray tracing IP, as in they added the second version of the ray tracing functionality in their third version of RDNA. So there's two things that they do differently. So one is, there's a couple of things, but one is, the reason why I'm saying ISA is like not documenting stuff. They actually use this intrinsic called image deviation intersect ray 2.0 that is not documented. It's almost the same as 1.0, but it has this box heuristic mode, which I'm going to talk about in a bit. And then they have another thing called use hardware intrinsic, where they suspiciously say, oh, if you have this defined set, we are going to use this intrinsic called trace ray LDS stack init. Otherwise, we are doing software stack emulation. So this stuff is not documented in the ISA doc either, I believe, I think. Or maybe that part is. Let's actually double check. Oh, I think maybe this part is. Okay, yeah, this part is documented. So in the RDNA 3, they added an instruction to manage the per thread stack in LDS. This is the thing I was saying that, hey, you have to emulate the stack because you don't have stack. And so you have to spend some amount of instructions. It's not a lot, but it's like maybe 4 or 5 instructions to manage the stack pointer and to load stuff from the stack and things like this. Instead, here they just have an instruction that I guess like loads or stores to stack, I don't know, whatever it is. It's very, very hardwired to ray tracing operation. It specifically expects a specific like amount of data that you have to load, some alignment. They have some like last visited thing which accelerates the stack traversal. So essentially, if you think of that loop that goes over your manually allocated stack, this instruction allows you to skip a whole lot of operations that you have to like hand code when managing that loop. So a RADV driver doesn't use this at all, and RDNA 3 AMD driver does. So this means that if we go back to this diagram, this stack is now sort of hardware stack. I say sort of because, like, I mean, it's an instruction that still accesses the same memory that you could access manually, but it's like accelerating operations by using by doing the same operations basically in fewer clock cycles than the software emulation would do, right? So that's the first thing that we're missing. So that's like a problem. To get this back, somebody has to go in and patch RADV to like be able to use this, right? Like it should be possible, but like nobody has done this. The second thing that they have in the GPU is this 2.0 instruction. As far as I can tell, maybe there is more benefits of the 2.0 instruction. For example, maybe this divergence thing is only for 2.0 instruction for some reason. But the one important thing that the 2.0 IP does around this, as far as I can tell, is, oh, this could also be, okay. So the one important thing is this. Is this the one? Oh, this actually there's probably more benefits to the 2.0 instruction that I'm realizing. Again, because it's not documented, I haven't spent enough time to like dig into details. It's just, and you should document their ISA instead of like not documenting half of the ISA. It seems self-explanatory. But the one thing that was cool that we can actually try is this. So, the array box intersection on RDNA 2 returns you 4 results because there is 4 boxes in a box, sorted by T. This is this first diagram. I'm sorry the font sucks. I haven't found the full res image of this. T is this 1, 2, and 3 point that they reference. This is the distance along the array that the hit occurs at, and this is the distance where the array enters the box. In RDNA 3, they've added a couple extra modes that you can switch between, either using this 2.0 instruction or using bits in the descriptor of the BVH. I don't really want to fully explain this, but you can like set some bits in some places in memory to actually activate this behavior, even if you're using the old instruction. So they have the mode closest first, they have the mode largest first, which is whatever boxes you did hit, we're going to sort them by like the overlap with the array, by the distance the array travels through them. And the logic there is this. The further the array travels through a box, the more likely it is that you're going to find objects inside that box. If you're doing reflection ray tracing, then you actually want to hit the first object. But if you're doing shadow ray tracing, you want any object, any hit at all. Because of this, empirically, if you look at the largest boxes or largest like traces through boxes first, you're more likely to find a ray earlier, a ray hit earlier this way. And so this is, they explicitly say, oh, it's optimized for shadow rays. And then they also added the mode closest midpoint. This is also better in case you want a first hit, because if you look at this picture, they actually have this giant red box, and then 2 and 3 boxes are contained inside it, and this is like fine. This is how the BVH might be constructed. And in the closest first sorting order, you are first traversing this large red box, and then you traverse the 2 and 3 boxes. And if you look at the first object instead, despite the fact that like the ray hits it after it enters the red box, it might be more likely to find some specific object inside this smaller box earlier than, or like the first hit of the ray, the closest object to the ray origin is more likely to be located in the box 1 than it is in box 2, because in box 2, like it could be in this region, and then if you process, sorry, in box 1, like in this red box, it could be processed, it could be located in this region, and so if you process the red box first, you're more likely to find a hit, but then you will process this box, and then you'll find an earlier hit after this. So, why does this stuff matter? Does this stuff matter? It's hard to know exactly, because if we don't rebuild the driver and like the official driver and like disable all of the stuff, then we won't know. But what we can do is we can enable the largest first mode, or whatever we want. Yeah, the largest first mode in RADV. How do we do this? Well, obviously we can change RADV source code, right? And if you look at the source code for, so like you look for, this is called box sort, you look through box sort and GPURT, you find this beautiful enum that tells us closest to 0. It's like a 2-bit, shouldn't it be a 2-bit value? I'm now confused. Maybe it's a 3-bit value. Oh, they have, this is some virtual values. Okay. Yeah. There's 4 values, I think. I think this is the enum. The question is, how do you specify these? One way to specify this is through that 2.0 instruction, which we don't have access to and can't easily use. But the other way that you can specify this, if you look at box sort, is, let me find this. Oh, one moment. I kind of need to find it because, I think this is that, right? Yeah. There was another header where it was easier to see. Oh my God, where is this? This? Yeah. So, this is the structure of the BVH descriptor data. This is the class descriptor, more or less, that we pass to the driver, but like how it's actually implemented in hardware. There's a bunch of like weird encoding here. They have a 40-bit address because the GPU doesn't support the full 64-bit address anyway, so not worth spending more bits on. Then there's this 15-bit reserved value. And if you look at the ISO docs, they do not document any new additions. If I can get back to this stuff. No. Image BBH. Okay. So if you look at the ISO docs, they just say here's 15 bits set to 0 after the base address. And indeed, there's 15 bits set to 0 after the base address. But 40 plus 15 is 55. If you look here at the, it's a union, so it's the same data. It's a struct called RTIP2+, so the IP2 version 2 of ray tracing stuff. There's 55 bits here, 53 of stuff, plus 2-bit box sorting heuristics. So instead of the 15 reserved bits, there is now only 13 reserved bits, and the top 2 bits are now used for box sorting heuristic. And you can just like change these bits and see what happens. So let's go to the RADV source, which I have someplace. And let me go back to, there's somewhere in RADV source that should be easy to find, maybe here, where they deal with the BVH descriptors. So there's this code that this is creating like intermediate representation for the assembly code. It's not quite the assembly code that executes on the GPU, but you see it creates a descriptor that essentially is then fed into the hardware instruction. There was always a bit, even in 1.0, to enable the sorting. So it does enable that. And if you look here, it's actually documented, it's this guy. If you set that to 0, the sorting is like completely disabled. But now they have this extra enum. And this extra enum should be in these bits 53 and 54 after, like in the base address, like 64-bit thing. But this value is represented as two 32-bit values. And so basically, this means that, like, 53 minus 32 is 21. And so at the bit offset of 21 in this same 32-bit value where this guy is, there should be a 2-bit value that controls the sorting mode. Now, I'm just going to hack this in. The actual behavior, as we saw, they have added 2 modes. One is best for one type of race, and the other one is best for another type of race. So the actual correct way to patch this is to take the shader that uses this and then patch the bits into the descriptor where they're used. And I think actually we actually just saw the code in the official driver that did this, I believe, in the compiler, like this guy. Yeah. This is the same. This is the similar code to what RADV uses. They also create like a fake descriptor or like descriptor data, but then they OR in these 2 bits shifted by 21, 2 bits shifted by 21 into the descriptor that they load from memory. And then they pass this to the hardware instruction, and then, you know, things are beautiful from there. Oh, in fact, maybe there's not, yeah, right. So there's not a 2.2 instruction probably. It's just the same instruction now reads more meaningful bits from the descriptor, but then the way they implement this in the official driver is by having 2 intrinsics, like 1.0 and 2.0. Okay, but the isodoc is still incomplete. If people from AMD are reading this, I already like told someone, but like, can you please fix the thing? I don't think there's a later one than Feb 23. If there is a later one, please tell me. That would be useful. But it would be like this stuff is under-documented because there's extra bits here that are meaningful. So the question is, does this matter for performance? And what I'm saying is we can actually try to answer this. So let's just add this to RADV, 21 bits. And I did this before on some previous stream, but to avoid like recompiling stuff too much, I'm gonna say, hey, if there's environment variable, let's like use this value as the box sort. Oh, and the one other thing is this stuff is compiled into the shader. This code is compiled into the shader. And so we have to disable the shader cache for this value to apply. Let's print something so that we know that the value is actually like respected. Okay, so now we can build the RADV driver and then disable RT emulation, build the RADV driver, and then as I was saying, disable the shader cache because otherwise like the value will not take properly. And then 0 is the value that's used by default because if you like there's just bits, right, that are 0 initialized. So this should be the same behavior that we had when we were running the code with RADV driver. And you can see the final pass is like 1.95 milliseconds. It's the same thing, right? So, oh, and this is our print. So now let's set it to 1 and hopefully it's faster. Aha, we set it to 1 and it's now 1.8 milliseconds. So we got 10% faster ray tracing for shadow rays just by flipping a bit in the descriptor. And the reason why RADV doesn't do this is it doesn't have this optimization. Again, the way optimization should work is it looks at the ray flags and say, oh, the ray flags say that you only care about the first hit, not the closest hit. Let's enable this flag. Out of curiosity, let's look at modes 2. 3 is disabled? Yeah. So in mode 2, it's now a little bit slower, I think, maybe like a couple % slower. But that again, that makes sense. We need, if we were doing ray tracing or like reflection tracing, our ray flags would say, oh, we want the closest hit. And in that mode, maybe we should have used the other thing, like the other mode. Box sort 3 is just disable sorting. It's probably slower. Why would you want to do this? I don't know. But I think they like migrated. No, it's the same performance. I think they migrated from having the boolean to having a boolean and an enum or something like this. Anyway, so this is the type of the optimization that RADV is missing because it doesn't know about the RDNA 3 ray tracing instructions. Actually, you know what? I'll leave this in. Maybe I'll only do a print. It's going to be my special magical RADV driver where you can accelerate ray tracing performance by 10% by just changing one bit. So that's the RDNA 3 stuff, right? So hardware stack, not supported by RADV driver. I can't hack it on stream because it's like too much, and it requires too much understanding of how the stuff works, and I will crash the GPU like 15 times. And then hardware array box sort mode, which again, as we saw, like at least 10% bump easily just with one bit. So this is one reason why RADV driver is slower than the AMDVLK driver. So the other reason is the BVH is different. It's hard to validate, like the algorithms of constructing the BVH are just completely different. It's hard to validate how much this matters comprehensively. One thing we can try to do, and I didn't actually do this, so I don't know what the results would be, but one thing we can try to do is this. Again, if you look at, we don't have enough time to like dig through the sources here, but there's a bunch of things that the official driver can do. One is it's called this like triangle compression, and also there's triangle splitting, which is kind of the triangle compression. I think it identifies pairs of triangles and like stores two of them in one node or something like this. I'm not sure. Triangle splitting can take one large triangle and build several boxes around this. Most of them, I believe, are disabled. There's too many settings in the official driver. Like the source code is not as nice to read, honestly, as RADV. But I think usually they are predicated on you enabling fast trace bit. We talked about this briefly last time when just doing the Vulkan setup, because when we build BLAS, you specify both BLAS and BLAS actually. You specify the flags. Oh, where's compaction here? You specify the flags, and when we specify the flags, we said we prefer fast trace, which means you want to spend more effort on building the BLAS versus sort of tracing the BLAS. You can also say fast build, which disables a bunch of optimizations like this, right? So this triangle splitting, triangle compression is like one pair of optimizations that are somewhat related. There's also this thing called rebraiding. I'm not sure exactly how it works. There is an Embry paper about this, you can read it, but I think broadly it refers to when you build class, you can like look at the nodes in BLAS that the class references. And so let's say if you have there's this classical ray tracing optimization that vendor docs usually mention, that if you have two objects with very overlapping boxes, then the ray tracing through this thing is less efficient because you trace a ray, it hits both of these boxes. Within every box, you have some set of triangles, like maybe like this here and maybe like this here, right? Like let's say you have one object kind of two halves split into two objects. This is not the ideal procedure for this. If you merge this in one, you would have, and then build a BLAS, you would likely have the top BLAS node split the object in roughly two equivalent halves like this. And that means that the ray would traverse less space because it would find the intersection earlier. So I think rebraiding refers to like when you build a class, you look at the top BLAS nodes and then you like incorporate them into the class as individual nodes instead of just like one object or something like this. Don't quote me on this. Point is, these optimizations are disabled when a bunch of flags are enabled. So one flag is fast build. And then there's another flag called allow update. Allow update, for example, this rebraiding that I mentioned, it's difficult to implement it when you want to update the structures dynamically, because you have to reshuffle a whole bunch of pointers instead of just being able to update the boxes. So what we can try to do is we can try to see what the effect is of enabling fast build or maybe allow update on BLASes and classes in both drivers. I don't know what the effect would be, but like we can see what happens, and then we'll see what the impact is. The compaction is an accident. I will talk about this in some later stream. So let's disable compaction. Let's do a run again. We'll just look at the final like shading time. So 1.95 something with RADV without compaction. 1.18, which I think is the same. Is it the same? Yeah, same as before on the official driver. So now let's try to, and just to be clear, like there's other differences in the algorithms that are not probably covered by flags, like the algorithms of building the BVH are just different. And it is likely that whatever the official driver implements is better, because my impression is the official driver is optimized more for ray tracing, because whenever people review AMD GPUs, right, they use the official driver on Windows to do benchmarks, and they say, oh, you know, you should buy this AMD GPU instead of this NVIDIA GPU because it's like the same in ray tracing or slightly slower in ray tracing, but faster in raster or whatever, right? Whereas with RADV, my understanding is it's just not as important of a use case, and so they haven't really looked at RDNA 3 as far as I can tell, right? So, so let's try to do fast build. This is BLAS, just for BLAS. Let's do just this first. I should be writing these numbers, but yeah, they're different. Okay, hold on. Let me write these numbers. So we'll have RADV, and we'll have AMDVLK, which is the official driver. So our baseline is the code that we had, in which case it was 118 and 197. Or rather 197 here and 118 milliseconds. So then with fast build BLAS the BVH size is the same. Interesting. Okay, so in the official driver with fast build BLAS, the performance drops to 138. In the official. In RADV, I'm not actually sure. It could drop in RADV because like they could also be switching algorithms or whatever. It drops a little bit as well, less so, but does drop. So then let's also try to enable. I think the worst case flags that you could have is fast build and allow update. KHR, please. Because it's kind of says spend as little time as possible on building the BVH, and also, by the way, I want to update it in the future. That's like the worst case, but maybe nothing changes. So RADV, it's the same, 205. And this is also 138. Cool. So let's keep this, and then let's do the same thing with class. Oh, with class we were using. Oh no, yeah. All that all makes sense. Okay. So this probably is less impactful, I would guess, but maybe disables rebraiding. And maybe rebraiding is already disabled through some other flags. I'm not sure. I haven't looked. Oh no. Oh yeah. Okay. 162. So this is fast build class in addition to fast build class. Let's just do updates as well, just to see. This is like a little important for us because we're gonna have to change. So that's the same. What if I do fast trace but allow update? Is it also bad? No. Okay. So this is just fast build versus fast trace. Interesting. Maybe this is not rebraiding, or maybe rebraiding is separate. So now let's look at RADV. I'm not even sure if RADV will change, but it might. Yeah, RADV barely changes. It's like 2.07 or something like this. I don't know. And then without this, it's probably the same. Yeah. Okay. So this is the numbers that I was writing down. So you can see that going for fast build for BLAS is substantially slower on AMDVLK. Like it seems to disable a bunch of optimizations that they're doing around BLAS builds, and it's like less slow on RADV. And then with fast build class, it's like a very small reduction on RADV, but a further significant reduction in AMDVLK. I bet this is rebraiding. But how do they do updates? Oh, updates on rebraiding should be fine. I bet this is rebraiding. Let's check. Or it could be just completely separate thing, not related to specific optimizations. I'm not sure. Again, this source code is like annoying to read. I'm sorry to people from AMD. Please document the ISA. But it's like there's too much. It's too ungrabbable. Like every word occurs in too many places, and there's too many options for everything and stuff like this. It's like, it's annoying. So that's when we build BLAS. That's fine. The question is how does rebraid type get determined? What does it depend on? It could be completely unrelated to rebraid. I have no idea. Oh, this looks like some decision tree. Let's see. If you're doing the top level build without the updates, oh wait, I think I recognize some of, oh wait, is this seemed useful. Hold on. Rebraid type. No, this is not as useful as I thought. Because there's like the build config and device settings, and like everything has rebraid types. And it's like, man, give me a function. So no, this is going from build config. I don't like this. So this is from build config to build settings. All right. Let's hope that this, no, this. This is useless. Okay. You know what? I don't care enough if it's like rebraiding or not, I guess. It might not be because it looks like update allowed controls rebraiding. Oh, let's try to set, prefer fast trace and update allowed in both. Or do we already do this? We already do this. Okay, so it's probably not rebraiding because this wouldn't act. All right, you know what, whatever. It doesn't matter if it's rebraiding or not. What matters is clearly the slowest RADV can get if you disable like all optimizations for BVH is, what is this, 5%? From here to here, it's a 0.1 millisecond difference, which is about 5%. The slowest AMDVLK can get is 50%, right? Presumably this means AMDVLK has more optimizations that you can disable. One other thing that might be cool is, let me run the box sort thing again with all of these penalizing things on RADV. Yeah, that is the correct, yes, okay. 1, I think. Oh, but I have to disable the shader cache, sorry. Okay. $197 again, interesting. And this is with all of the horrible BVH flags, right? No, this is not with the horrible BVH flags. Okay. fast build. There's too many flags to keep track of, so maybe some numbers I wrote are slightly bogus. Okay, so this is the correct configuration. All right, yeah, 195, I would even say. So when using box sort on RADV, like we can recover 5% of performance on top of the law. Anyway, like this, it might be essentially that if RADV had a better BVH, then it could be, and the box sort, then it could be a full, like, I don't know, 40-50% faster than what it is, plus add the software stack management that I was talking about, and maybe that gets all the way back. Like, it should be possible to do the same performance because it's just code, right? It runs on top of the same GPU. Anyway, so that's kind of it. Essentially, it's kind of getting to the bottom of the performance differences. I think this is it. We don't really, it's like already more than 3 hours stream now. So we don't really have time to look more into this, but the upshot is this. Until RADV sort of fixes some of these problems, I could try to, box sort mode is the one thing I could try to contribute to patch for myself, because that's like relatively straightforward. I don't know about the stack stuff. It's like a lot of, well, maybe the stack stuff isn't too bad, I'm not sure. And definitely the BVH, I don't really want to look into. It's too much code into like a code base that I'm not married to. But for this stream, for the foreseeable future, we are going to switch to the AMDVLK driver because it has way more mature ray tracing support from the performance perspective, which we care about now more than we care about other things. So where does this leave us? Let's see, let's disable all of this stuff. And then we might do, I don't want to do a ray tracing tool trace because we don't have enough time and it might crash, semi-crash the stream again. But like where we are right now is we have okay performance. It's not like perfect, it's not optimal, but we have decent performance. We're doing 1 ray per pixel, and again, we could do 2 rays or 3 rays per pixel within our performance budget. And there's 2 ways to go from here. One is we can flesh out the material story. We can do like reflections, we can do actual specular, which is probably easier, etc. And the other one is we can do more than 1 ray per pixel for various effects, which then requires denoising to sort of maintain performance. I'll think about what would make sense before. I know little about denoising. I was gonna try to do like restir instead of using any off-the-shelf denoisers. Off-the-shelf denoisers are not super fun because they're all like complicated and it's a lot of code to integrate and stuff like this, and it's just not like very interesting. But it might be complicated, like it might take more than 1 stream to even get a basic version working, who knows. So I'll think about what to do next, and then I might do some cleanup work off stream, but that's kind of where we are. I think we are in decent spot to flesh out the ray tracing support. Oh, right, and the one basic thing that we are not doing yet is ray tracing of transparent objects, translucent objects, transparent objects. For this to work, we basically have to be able to trace a ray, and then a ray hits a triangle, and then we look at this triangle's UV coordinates and the texture map if it has an alpha texture, and then we sample it, and then we proceed or not proceed with the ray based on what we find. This is going to make our performance worse, so we might do this before or after some of these other things I have not decided yet, but this is what I want to do in the future as well. So that's kind of the plan, and that concludes the actual stream. I'm gonna look and chat and like answer whatever questions there are, and then we'll end this stream. There is not, we are going back to the cadence of at most 1 stream per week. So there is probably going to be a stream next weekend. I haven't decided yet what it will be about, but it's going to be about something. So that is that. Let's see. So there might be a newer version than Feb 2023. Whoa, 3.5? What the heck is 3.5? Is 3.5 the PlayStation thing? What is 3.5? Did I get the naming wrong? Is it 3.5? What is 3.5? So of course they don't reference any specific model numbers. Let's look at ray tracing. I saw 3.5 as an informal description of yeah, this doesn't document any. This looks the same. I saw 3.5 as an informal description of the like PS5 Pro hardware, whatever the heck is in there, but maybe this is a different 3.5. Interesting. Okay, so good to know. Thank you. But yeah, this looks like it's the same. Is there more? No, there is not more. Let's see what Phoronix says about this. Oh, I see. This is Strix Point. Okay. So that should be like after, I'm guessing, the GPU that I have. I wonder what the differences are. Do they have like, here's what has changed since 3.0? Because they used to do this in some specs, I think. Let's see. Nah, there's nothing super obvious here. Oh, one thing I should quickly check, by the way, is I have checked it before on the Blitz shader, but I haven't checked it on the ray tracing shader, is what's the optimal wavefront size. So this is 1.18 milliseconds for the final pass. Let me just very quickly, 8x8 is 64 already. Let me do an 8x4. This is unlikely to be good, but you never know. Okay, this is basically the same. It's actually maybe 0.5% better. And then let's try to do 16x8. It's probably going to be worse, but yeah. Yeah. There's two conventional wisdoms for sizing these things. One is go with the size that just fits the GPU wavefront. So RDNA GPUs go 32 or 64. So this would be either 8x8 or 8x4. Or go pretty big so that the driver has freedom to optimize things, but like that never happens. So this is probably good. Oh, the other thing we could try is non-square versions, but yeah. There's also some other ways to like try to optimize stuff around this with how memory access works, but it doesn't look like, yeah, it looks like we are good with 8x8 for now. Okay, it's an extra new line that is not necessary here. Let's see. Yeah. AI chips. AI chips. All right, so that is it. I don't think there's anything else in the chat. Yeah, I think I covered everything. So thank you for attending the stream. That is it. We now have a decently competent performance-wise ray tracing implementation. There is a ton of stuff to do with ray tracing. We haven't done compaction yet, although that doesn't really matter for performance, I don't think. There's some other things I'm not sure yet around BVH construction to the extent that we have freedom to optimize it. And then, of course, there is the denoising. Denoising implies a number of rates per pixel is different from one, either less or more. There's like translucency, reflections, etc., etc. There's like a bunch of, we have only started with ray tracing support, so there's a lot further that we could take it in. Like even reflections are interesting. So let's say you do reflections, right? So obviously we can take the camera, like right now we could take the camera position, we can reflect the ray from it to the world position around the normal. We can fetch a ray in that direction, and then we can look at the object. And then the question is, what do we do next? We need to sample the texture on this object to even have a rough idea of what color should be reflected, right? So for this, we already have to implement the access to geometry and texture fetching and stuff like this that I was talking about. But then, okay, you have the albedo of the object. Okay, cool, that's fine. Maybe you even have the normal. Okay, maybe that's fine. So maybe you can do a basic shading of the reflected value. The question is, what if the reflected object is in shadow and your object is not? Ideally, you should like compute that. Of course, to compute that, you have to trace another ray from that object, like somewhere. And then there's questions about lighting and stuff. So like reflections can be anywhere from one extra ray per pixel or fewer if you don't, like if you do denoising, to like a lot of rays per pixel because you have to do shadows and lights and stuff. Oh, and like light sources is the other thing that's in my plans with shadows and light sampling and stuff like this. But we are entering a territory where there's fewer Vulkan specific things to look into and more like general graphics programming things to look into that I'm not actually like an expert in at all. Like I know some of the basics around like how raster works and like multiple importance sampling that you need for lights and stuff like this, but I know few details, very few details, and I've never done this before, so like we'll see if that makes sense for me to explore on stream or not. So that is it. Oh, and at some point we'll have to do proper LODs for ray tracing. Right now there's this problem where the ray tracing data is always LOD 0, but the further the object is from the screen, the rendered object is like not 0. I have this button that makes the rendered LODs worse, and if I set it to like 2 or something like this, you can see that on this bike, there's now self-occlusion for shadows, like self-shadowing, but like incorrect. And that's because the pixels on the rendered geometry are like under the real geometry. And so ideally the way you fix this is you rebuild class every frame based on LODs, but that requires more geometry to be fed into the BVH builder. And I don't know if I want to do this. It's already like hundreds of megabytes. It's already, we have to do compaction. Compaction like makes things better. I think with compaction on the official driver, it's like half of the uncompacted BLAS. So this means that we will have 140, 150 megabytes of geometry right now in optimal setup, which is already more than all of the data that we have for both rendering paths for rasterization. And that's like, it could be worse. It will be worse if we do LGs in ray tracing. So I don't know yet if I want to do these things, but like we'll see. Anyway, thank you for attending the stream. Let's see what the stream is going to be about next week. As usual, socials will have the announcements. And bye.